Something strange happens when you think about time. We move through it, yet we can't touch it. It rules our lives, yet no one's ever seen it. It ticks, it flows, it passes. But what exactly is time? Tonight, we drift into the mystery of time itself, from the ticking clocks that govern our days to the infinite stretching fabric of the universe. You might fall asleep before we're done, but that's okay. Time doesn't mind. Tell us in the comments, where are you watching from, and what time is it for you right now? And if you love drifting off to deep science, go ahead and subscribe. There's always more to explore. Close your eyes, and let's begin. Chapter 1. What is time? Time. It's a word we say every day without thinking. What time is it? I don't have time. It's time to go. But for something so ordinary, so constantly present in our speech and thoughts, time is one of the strangest and most elusive concepts we've ever tried to understand. We step back for a moment, strip away the clocks, the calendars, the numbered hours and dates. What remains? What is time when you remove all the tools we use to measure it? That's the question. And the more you look at it, the more confusing it becomes. Time, at its most basic, seems to be a measure of change. We notice that things are not the same as they were before. A leaf that was on a branch is now on the ground. A cup that was whole is now shattered. A child grows into an adult. The stars shift position across the night sky. Change gives us the illusion of movement, of flow. And that movement we call time. But is it actually moving? Or is that just the way our brains make sense of experience? Ancient humans didn't have atomic clocks or precise seconds. They had the sun and the moon, the tides and the seasons. They noticed patterns, cycles, things that returned. Day followed night, winter followed summer, and life followed death. From these patterns they carved time into chunks. They divided their experience into periods and phases. But was that time, or was that just motion? Even today, when we measure time, with lasers and cesium atoms vibrating billions of times per second, we are still only measuring change, a consistent pattern of change. We call it time because it feels like something is passing, but all we're doing is comparing one repeating event to another. Your heart beats, your breath rises and falls. The Earth spins once every 24 hours. We label this motion with units, but time itself remains undefined. Sir Isaac Newton thought time was absolute, a giant cosmic clock that ticked the same for everyone, everywhere. In his view, time existed independently of the universe. It was the grand background against which everything happened, a kind of invisible stage. But in the early 1900s, Albert Einstein shattered that view. He showed us that time isn't fixed. It's not absolute. It bends. It stretches. It warps under the influence of speed and gravity. According to Einstein's theory of special relativity, time flows differently depending on how fast you're moving. If you travel near the speed of light, time slows down for you, relative to someone who remains still. And in general relativity, Einstein's theory of gravity, time slows down the closer you are to a massive object like a planet or a black hole. This effect is not imaginary, it's measurable. Your head ages slightly faster than your feet, just because it's farther from Earth's center of gravity. So now we had a different view. Time was no longer some universal tick-tock. It became a flexible part of a larger fabric space-time that could be bent, curved, and distorted. Imagine a giant sheet with balls on it. The balls create dips, and if you roll something across the sheet, it curves around them. That's gravity. And time is a direction on that sheet, one of the threads in its weave. But here's where it gets even stranger. Quantum physics, the branch of science that deals with atoms and particles, treats time completely differently. In quantum mechanics, time doesn't bend or warp. It just sits there, a background parameter, something we plug into equations to predict what particles will do. But those particles don't experience time the way we do. They don't have a clear before and after. They exist in a haze of probabilities, and only when we observe them do they snap into a specific moment. This leads to a deep contradiction. In one framework, relativity, time is dynamic. In another, quantum mechanics, time is passive. Scientists have spent decades trying to unify these two views. They've tried building quantum gravity theories, string theory, loop quantum gravity, but time remains a stumbling block. So let's ask a different question. Is time real? It might seem silly to even ask. Of course, time is real. We age, we remember, we plan. But some physicists and philosophers argue that time is not a physical thing. It's a concept, a useful illusion. Our brains, after all, are built to notice change. We evolved to detect danger, find food, anticipate movement. So we developed a model of reality that includes before and after, cause and effect. But that doesn't mean time exists outside our minds. Some theories go even further. They say all moments past, present and future already exist, that the flow of time is an illusion. We feel like we're moving through it, but really we are just experiencing slices of a giant unchanging block. This idea is called the block universe. In it, time is just another dimension, like space. You can point to a place on a map. In the same way, you could hypothetically point to a moment in time. We feel the now because our consciousness moves through this block, but the block itself never changes. This is hard to accept. We feel time so deeply. We feel memories in our bodies. We fear the future. We long for the past. But what if those feelings aren't caused by time? What if they are time? Think about this. We never actually experience the past or future, only the present. Everything else is memory or imagination. Even the present is a blurry concept. Our brains take time to process information. The image you see now actually happened milliseconds ago. You live in a constant delay, a smooth hallucination of now. This suggests that time as we feel it is not an external force. It's a story, a narrative we tell ourselves, stitched together from sensory data, memory, and prediction. The neuroscientist David Eagleman once said, "Your brain is a time machine, and it's one that cheats." He meant that your brain compresses, stretches, and distorts time constantly. Time flies when you're having fun. It crawls when you're bored. Traumatic events seem to take forever. Days can vanish in the blink of an eye. None of this is about the outside world. It's about the way your mind constructs experience. But if time is just a story, why does the universe behave as if it has direction? Why do eggs break but never unbreak? Why do we remember the past but not the future? This is where entropy enters the picture. Entropy is a measure of disorder. In any closed system, disorder tends to increase. A neat room becomes messy. A hot cup of tea cools down. Things fall apart. This trend toward disorder gives time its arrow. We know which way time is pointing because we can measure the increase of entropy. It's one of the few truly irreversible things in physics. Interestingly, the fundamental laws of physics don't care about direction. They work just as well forward as backward. You can run most equations in reverse and get a perfectly valid result. So why don't we see broken eggs reassembling themselves? Because it's so improbable. Not impossible, just unimaginably unlikely. The number of ways to be disordered far exceeds the ways to be ordered. So over time, systems evolve toward more disorder, and with that disorder, we feel time's flow. But this raises another mystery. If the universe is heading toward maximum disorder, why did it start in such a low entropy state? That's one of the deepest questions in cosmology. The early universe, just after the Big Bang, was incredibly smooth, uniform, and low in entropy. Why? No one knows. But this special initial condition may be the reason we experience time at all. Without it, there might be no arrow, no direction, no flow. So here we are, conscious beings floating on a tiny planet, in a universe where time may be real or not. We measure it. We fear it. We chase it. We waste it. We feel its pressure like a weight on our chest. But we still don't know what it is. Time is both the most familiar thing in our lives and one of the most alien. It connects our memories, defines our hopes, and sets the rhythm of the cosmos. And yet, it may not even exist, at least not in the way we think. Chapter 2. The Arrow of Time. If time isn't just a clock on the wall, if it's not merely the ticks and tocks that structure our days, then what is it really that gives time its direction? Why do we feel it flowing only one way, from the past into the future? You don't remember tomorrow. You don't wake up to find yourself growing younger. Events unfold in a particular sequence. A match is struck, and then it burns. Never the reverse. This one-way feeling, this asymmetry, is what scientists call the arrow of time. But here's the mystery. The fundamental laws of physics, from Newton's equations to quantum mechanics, don't care which way time flows. If you filmed two atoms bouncing off each other, and played that video in reverse, you wouldn't be able to tell the difference. The math would still be correct, the behavior still legal under the laws of physics. And yet, in our world, some things clearly happen only one way. Eggs break, but don't reassemble. Smoke disperses but never recoalesces. Memories are formed, not predicted. Why? To understand this mystery, we need to talk about entropy. Entropy is a measure of disorder. It's a way to count how many possible ways a system can be arranged. A neat, organized room has low entropy, only a few specific arrangements. A messy room? High entropy, countless ways to be disorganized. The second law of thermodynamics tells us that in a closed system, entropy will always tend to increase. This law is not based on force or motion, but probability. There are simply far more disordered states than ordered ones, so if you let things evolve naturally, they'll drift toward chaos, not because they have to, but because that's what's most likely. Imagine dropping a deck of cards perfectly sorted by suit and number. Once it hits the ground, the chance of it landing back in perfect order is astronomically small. Not impossible, just profoundly improbable. That movement from order to disorder, from low entropy to high, is the arrow of time. It's not built into the equations of physics. It emerges statistically from how likely certain configurations are. In other words, we see time flowing forward, because disorder increases, because broken glasses outnumber unbroken ones. But this raises another deep question. If everything tends toward disorder, why was the universe so ordered at the beginning? The early universe, just after the Big Bang, was surprisingly uniform. Particles were evenly distributed. Temperatures were nearly the same everywhere. There was low entropy. That's unusual. It's like finding a shuffled deck of cards that happens to be in perfect order. This strange initial condition is still one of the greatest unsolved problems in cosmology. Where did the arrow of time come from? Why did time begin with order, rather than chaos? Some physicists argue that the Big Bang wasn't the beginning of time, but the beginning of the arrow. Before it, there was no direction, no before and after, just timeless. Others suggest our universe is part of a larger system, where time flows in different directions in different regions, like opposite arrows sprouting from a central point. In that case, somewhere out there may be beings who experience time in reverse. For them, our future is their past. But let's return to entropy for a moment. You might think of disorder as messiness, but it's not quite the same. Entropy doesn't mean chaos. It means more possibilities. A gas that spreads through a room isn't chaotic. It's simply occupying more positions. The reason we associate entropy with decay or aging is because our bodies and machines rely on structure, on maintaining low entropy states. As entropy increases, those structures fall apart. A candle burns down. A phone battery loses charge. We wrinkle, we tire, we decay, and all of this makes time feel real. But now, let's flip the script. What if we could reverse entropy? Would time reverse with it? If we could perfectly track every particle in a room and move them backward in exact detail, we could, in theory, return a broken vase to its original state. The entropy would decrease, and to us, it would look like time going backward. This is the premise of Loschmidt's paradox. If physics is time-symmetric, why don't we see these reverse miracles happening naturally? And again, the answer is probability. The odds of every particle cooperating in reverse are so absurdly low that they might as well be zero. It's not forbidden, it's just unfathomably unlikely. Now think about memory. You don't remember the future, only the past. Why? One theory suggests that memory is the brain's way of recording low entropy events. As entropy increases, we gather information about what came before, but not what comes next, because it hasn't yet increased entropy enough to leave a mark. In this view, the arrow of time exists because memory exists. Or perhaps, memory exists because entropy is direction. Even our language reflects this. We say we look forward to things, we leave things behind, we move on. Time is embedded in the way we think, feel, and speak. But in reality, the universe doesn't move. It just is. All we ever experience is the shifting state of configurations, the change from one arrangement to another, and we call that shift time. There's another idea worth exploring here, the psychological arrow of time. That is, how we perceive time subjectively. From a physics perspective, A process could run forward or backward. But for us, it always flows one way. Our minds are wired to build a sense of continuity, of before, now, and after. That narrative creates a psychological direction, and that direction aligns with entropy, because our memories are formed in lower entropy states. We remember what has already happened, not what hasn't yet increased entropy enough to register. But this arrow is deeply personal. People who suffer from certain neurological conditions lose their ability to perceive time properly. For them, events blur together, moments stretch or collapse. The arrow becomes fragmented. Even in ordinary life, time perception varies. When we're frightened, time seems to slow. When we're bored, it drags. When we're in love, it flies. These shifts aren't just poetic, they're measurable. Your brain adjusts its internal clock depending on context. Your heart rate, breathing, and attention all influence your experience of time. So perhaps the arrow of time is not one arrow, but many. Some physical, some mental, some emotional. And they all point forward, because that's the way entropy rolls. Let's imagine, just for a moment, what it would be like to live in a world where time flowed backward. You'd remember tomorrow instead of yesterday. You'd grow younger, you'd inhale carbon dioxide and exhale oxygen. Coffee would unbrew itself, and conversations would begin with goodbyes. It sounds bizarre, and it is. But according to the laws of physics, this world is not illegal, just improbable, and it would feel as normal to its inhabitants as our forward-flowing time feels to us. This challenges our deepest assumptions because time is not just a feature of the universe, it's the lens through which we experience the universe. If you changed the direction of time, you wouldn't just change events. You'd change the meaning of everything. Cause and effect would reverse. Choices would unhappen. Memories would become prophecies. And you wouldn't even notice, because your consciousness would flow with it. In the end, the arrow of time is not a single sharp direction. It's a pattern, an emergent property, built from probability, decay, perception, and change. It's not etched into the equations of physics, but it's etched into every breath we take, every footprint we leave, every memory we carry. Entropy rises, and so do we, moment by moment, along this strange, invisible path, not because time pushes us forward, but because it's the only direction left to go. Chapter 3. Einstein's Time. When Space and Time Merged. In the early 20th century, one man changed our understanding of time forever: Albert Einstein. Before Einstein, time was thought of as absolute, a universal clock ticking the same for everyone, everywhere. Time was something you could count on, steady, unchanging, independent of who you were or where you stood. It was Newton's time, a rigid, cosmic metronome, always in sync. But Einstein saw something else. He saw time as elastic, and that changed everything. In 1905, Einstein introduced the world to his special theory of relativity. He was only 26 years old. The theory began with a simple but radical idea. The laws of physics are the same for all observers, no matter how fast they're moving, and the speed of light is constant, no matter how fast you're going. This had strange implications. If you're on a train moving close to the speed of light, and you shine a flashlight ahead, you would still measure the beam of light moving away from you at the same speed, and so would someone standing on the ground. How is that possible? The answer is that time must change. To make the math work, to keep the speed of light constant, time has to slow down for the person moving. This phenomenon is called time dilation. It means that moving clocks tick slower, and this isn't just theory. It's been tested. In experiments, scientists have flown atomic clocks on airplanes. When they return to Earth, the clocks show slightly less time than the ones that stayed behind. Just nanoseconds, but measurable. Time literally passed slower for the moving clock. This idea challenged everything we thought we knew. Time wasn't a universal drumbeat. It was personal. It depended on how fast you were moving. Two people, moving at different speeds, could disagree on how much time had passed, and both would be correct. The faster you go, the slower your time ticks, relative to someone moving more slowly. And it gets weirder. Special relativity also revealed that time and space are not separate. They are one fabric. Space-time, distance and duration blend together, depending on how you're moving. The faster you go through space, the slower you move through time. This leads to strange paradoxes. Take the famous twin paradox. Imagine two twins. One stays on Earth. The other travels on a spaceship at near light speed, then returns. To the one on the spaceship, the trip takes just a few years. But back on Earth, much more time has passed. Decades, maybe. The traveling twin returns, younger than the one who stayed behind. This isn't science fiction. It's a consequence of the math. And in particle physics we see it all the time. Fast-moving particles live longer than their slower counterparts from their own perspective. But Einstein wasn't done. 10 years after special relativity, in 1915, he published general relativity. It took the theory further into the realm of gravity. And here's where time gets even more distorted. General relativity showed that gravity is not a force pulling objects downward. It's the curvature of spacetime caused by mass and energy. Big objects, like planets and stars, bend spacetime around them. And that bending affects how time flows. Closer to a massive object, time slows down. Farther away, time speeds up. This is called gravitational time dilation. If you placed a clock at the top of a mountain and another at sea level, the one at the top ticks slightly faster, because it's farther from Earth's mass, where spacetime is less curved. Again, this is not theoretical, it's measurable. GPS satellites orbiting Earth experience less gravity than we do on the surface, and their onboard clocks tick faster. Engineers have to account for this time difference. Otherwise, your GPS location would drift by kilometers every day. Now imagine a black hole, an object so dense that its gravity bends spacetime to the extreme. Near a black hole, time slows dramatically. Get close enough to the event horizon, the edge where nothing escapes, and time essentially stops. From the perspective of someone far away, you could hover near that horizon, wait a few minutes, and when you return, thousands of years might have passed elsewhere. That's not just a wild idea for movies, it's built into the equations of general relativity. To an outside observer, you would appear frozen, infinitely stretched in time. But to you, inside that gravity well, time would feel normal. This is one of the strangest things about time. It's not absolute, it's relative. And even though we all feel like time flows uniformly, the universe disagrees. Let's pause and imagine space-time, not as an empty vacuum, but as a soft, stretchy fabric. Planets and stars rest on it, pressing down, creating dents. Light bends around these dents. Clocks slow near them. Everything moves along curves in this warped landscape. This visualization helps us grasp the essence of general relativity. But what makes it remarkable is how well it works. From predicting the orbit of Mercury to detecting gravitational waves rippling through the cosmos, Einstein's vision continues to be confirmed. And it all depends on time behaving differently, depending on where and how fast you are. So time is not a river flowing the same for all. It's more like a landscape shaped by motion, mass, and energy. Wherever you are in the universe, your time is slightly different from everyone else's. The difference may be too small to notice, but it's there. Every person, every object, every particle, all ticking at their own rate, depending on their position and velocity. And yet, with all this warping and stretching, you might wonder, why don't we notice? Why does time feel so smooth, so uniform? The answer is scale. In daily life, the differences in time flow are minuscule, too small to detect without precision instruments. We're all moving at similar speeds. We all live in the same gravitational field. So, the variations are drowned out by our shared environment. But zoom out, travel far, move fast, time begins to twist. And it's not just theory anymore. We've seen it in the lab. We've built technology that depends on it. There's a quiet wonder in this, that two people can live side by side, their watches synced, but deep down, their time is already diverging. If only by fractions of a second. And if one of them were to leave, and travel far through curved space at high speed, their story would unfold more slowly. Their clock would tick differently. Their now would become another's then. Einstein's legacy is not just math and equations. It's a new understanding of reality, where time is no longer a backdrop, but an actor on the stage. It bends, it stretches, it interacts, and it cannot be separated from space. Together they form the stage, space-time, on which the universe plays out. Everything we do, every moment we live, every memory, every possibility, takes place within this strange, dynamic framework. and the more we learn, the more time reveals its illusions. But what happens when we leave relativity and enter the world of the very small, when time isn't curved or slowed, but questioned entirely? That's where we go next, into quantum time, where even the idea of before and after begins to break apart. Chapter 4. Quantum time, when before and after blur. In the world of the very small, time begins to dissolve. Everything that felt stable in classical physics, cause and effect, motion, flow, starts to shimmer at the quantum scale. And suddenly, time isn't what it seemed. In the quantum world, particles behave strangely. They exist in superpositions, multiple states at once. They don't have defined positions or paths. They only become real when observed. And in this strange fog of probability, the role of time becomes unclear. In classical physics, we use time to predict motion. A planet travels through space over time, a pendulum swings from one side to the other, and we use time to describe its journey. But in quantum mechanics, we don't always know what a particle is doing in between observation. We can describe its initial state, and we can describe its final state, but in the middle, there is only a cloud of possibilities. This is the heart of the quantum mystery, and it raises an uncomfortable question. If we can't track a particle's journey through time, is time even a necessary ingredient? Let's look at one of the most iconic equations in science, the Schrödinger equation. This equation governs how a quantum system evolves. It tells us how the wave function, the cloud of possibilities, changes over time. But here's the twist. In the equation, time itself is not a dynamic variable. It doesn't change. It just exists in the background, a parameter we input, not something that in this sense, time in quantum theory is external. It's not part of the system being described. It's a clock outside the box, not a feature inside it. This stands in stark contrast to general relativity, where time is affected by mass and energy, and bends as part of spacetime. The two theories don't agree. One treats time as dynamic, the other treats time as fixed, and this disagreement has haunted physicists for decades. To unify these two perspectives to build a theory of quantum gravity, we need to resolve the role of time, and in some approaches, time disappears altogether. In the Wheeler-DeWitt equation, a proposal for describing the quantum state of the entire universe, time is absent. The equation doesn't include a time variable at all. This leads to the problem of time in quantum cosmology. If time isn't in the equation for the universe, how do we explain the apparent passage of time we experience? One possible answer is that time is emergent. Like temperature or pressure, it may not be a fundamental ingredient of reality, but something that arises from more basic, timeless ingredients. In other words, time may emerge from entanglement, from relationships between parts of the universe. When enough particles interact and enough correlations form, a direction appears, a pattern that looks like time. We feel it not because it exists independently, but because it emerges from the statistical behavior of countless interactions. This idea is deeply unsettling. We want time to be real, to exist outside of us, to move forward, reliably, like an arrow. But quantum theory whispers something stranger. Time, it suggests, might be like temperature, a macroscopic illusion born from microscopic chaos. And that illusion might not be universal. Some quantum systems appear timeless. They reach what's called quantum equilibrium, where change becomes undetectable. The system remains in a stable superposition, not evolving, not decaying, not aging. In such states, there is no before or after, only a kind of quantum stillness. And then there's entanglement, one of the most mysterious features of quantum mechanics. When two particles are entangled, measuring one instantly determines the state of the other, no matter how far apart they are. This seems to violate time itself. The influence happens instantaneously, faster than light, suggesting that cause and effect may be local illusions. But entanglement doesn't allow communication. It's not that information is sent, it's that the system is one whole. So the division into parts, into this particle here and that one there, might not be as real as it seems. This connectedness hints that our separation of events into moments, into sequences, may not apply at the deepest level of reality. And then, there's the quantum measurement problem. When we observe a particle, its wave function collapses, it chooses a single state. But when exactly does this happen? And how does time play a role? Is the collapse instantaneous? Is it spread over time? Does time even make sense at this scale? Some interpretations suggest that what we call collapse is not a real process, but a shift in our knowledge. Others, like many worlds, say there is no collapse, all outcomes happen in parallel universes, each with its own branching timeline. In that case, time doesn't just move forward, it splits. Our experience of time in this view is just one thread through a vast multiverse. Each decision, each random quantum event creates new branches, and we ride one branch feeling time move, while in the greater whole, all paths coexist. It's a poetic idea, and it makes time feel both infinite and insignificant. But again, the math doesn't tell us which interpretation is real. Quantum mechanics works. It predicts results with stunning accuracy. But what it means, that's still a matter of debate. Even more bizarre are experiments with delayed choice. In some setups, the decision to observe a particle can be made after the particle has already entered the experiment. And somehow, the particle seems to know whether it will be observed in the future, and adjusts its behavior accordingly. It's as if the future influences the past. This doesn't allow paradoxes. It doesn't violate causality. But it suggests that our classical idea of time, with a clear cause leading to a later effect, might not hold in the quantum realm. Instead, the universe may operate as a whole, not just forward through time, but in a kind of holistic pattern, where all parts are connected, and time is just a convenient projection. This leads some physicists and philosophers to suggest that the flow of time is a psychological illusion. Our minds are built to detect changes, to remember the past, to expect the future. But in the quantum world, where particles have no definite paths, and systems evolve without clocks, time may not exist as we imagine it. It may not even exist at all. And yet, we do experience it. We grow older, we remember, we forget. We live inside moments, one after another, as if they were laid out in a line. This contradiction between the timeless nature of quantum physics and the relentless flow of human experience is one of the deepest puzzles in all of science. How do we reconcile the two? Some researchers are now exploring quantum time crystal structures that repeat in time, not just in space. These hypothetical systems could maintain motion without energy input, like a pendulum that swings forever without losing momentum. If they exist, they might help explain how time could emerge from quantum systems. Other scientists are building quantum simulators, trying to recreate space-time itself from entangled particles, as if space and time are not backgrounds, but networks of relationships. And slowly, patterns begin to appear. Clocks made from complexity, time born from entanglement, moments built from information flow. It's early, the results are murky, but the direction is clear. Time may not be a container, it may be a consequence. In the end, quantum physics forces us to ask hard questions. What is time, if the deepest laws of the universe don't seem to need it? What is now, if the past and future blur at the smallest scales? And who are we, if the thread we follow is just one among countless branches, splitting forever into possibility? These aren't just abstract ideas, they touch everything, from how we understand the Big Bang, to how we define consciousness, to what it means to exist at all. In the quantum world, time is no longer a river. It is a fog, a set of relationships, a structure that emerges only when enough complexity arises to demand it. It is not fundamental, it is not guaranteed, it is not simple, and yet, it is the rhythm of our breath, the beat of our hearts, the story we tell ourselves to hold the universe together. And in that story, there was a beginning, a cosmic moment, when time as we know it may have begun. Chapter 5. Before time. What existed before the beginning? Time begins with a question. Not what is it, but when did it start? We look back at the universe, at galaxies racing away from each other, at cosmic microwave echoes frozen into the sky, and all evidence points to a beginning, about 13.8 billion years ago, the Big Bang. A moment when space, matter, energy and time itself came into being. Or so we think. But what does it mean to say that time began? What came before that? Can you even use the word before if time didn't exist yet? To explore this, we need to tread carefully, because we are walking a fine line between physics and philosophy, between data and speculation. But let's begin where we can, with what we know. According to general relativity, the universe began as a singularity, the point of infinite density and temperature, where the laws of physics break down. This is not just a guess. It's what the math tells us when we trace the universe backward, using Einstein's equations. As the universe expands today, we can imagine rewinding that expansion. Galaxies get closer, temperatures rise, space shrinks, and time compresses, until finally, we reach a limit, a moment where space and time curve so extremely they collapse into a single unknowable point. But singularities are signs of failure. They're not real things. They're places where our current theories stop working. They tell us that we're asking a question our tools can't yet answer. So what happened at the beginning? Was it really a singularity? Or is that just a symptom of trying to describe quantum reality with classical equations? This is where quantum gravity comes in. If we could combine general relativity with quantum mechanics, two powerful but incompatible theories, we might get a clearer picture. And in some versions of quantum cosmology, the singularity disappears. Time doesn't begin abruptly. It emerges smoothly. One proposal is called the no-boundary hypothesis, introduced by Stephen Hawking and James Hartle. In this model, time near the Big Bang becomes indistinguishable from space. There is no beginning in the traditional sense. Instead, time curves gently into existence, like the South Pole of Earth. There's no point further south than the South Pole, not because there's a wall or a border, but because direction itself becomes undefined. Similarly, at the beginning of the universe, there was no before. Time simply didn't exist, and then it did. This idea is difficult to grasp. Our minds are wired to think in sequences, this, then that, cause, then effect. But here, cause and effect may dissolve. There may be no earlier from which the universe sprang. Time, like temperature or pressure, may have emerged as the universe expanded and cooled. Another idea is that the Big Bang wasn't the beginning, but a transition, a bounce. In cyclic universe models, the cosmos expands and contracts in endless cycles. Big Bang, expansion, collapse, repeat. Each cycle erases the memory of the one before, leaving behind only a new arrow of time. If this is true, our universe may be just one chapter in an eternal cosmic story, each beginning preceded by an end, each end paving the way for a new beginning. Still, we return to the same mystery. What is time? If it didn't exist until the universe began, can we ask what came before, if the word before doesn't apply? It's like asking, what's north of the North Pole? The question feels meaningful, but it isn't. It points to a direction that simply doesn't exist. So perhaps before the Big Bang is not a real concept, not because we lack knowledge, but because the question itself has no reference point. But human curiosity isn't easily satisfied. We push forward anyway. Some cosmologists suggest the universe was born from a quantum fluctuation, a spontaneous, random blip in a timeless void. In this view, the vacuum isn't empty. It teems with potential. Particles, energy, even entire universes can emerge from this sea of possibility. It's not nothing. It's a quantum foam, a state of pure potentiality. Our universe might have bubbled into existence from this timeless field, not as a cause and effect event, but as a spontaneous configuration. And with that configuration came time. It's a radical idea, that the universe created time as part of its own birth, that what we call before is not earlier, but elsewhere. That time isn't something that stretched infinitely backward, but something that unrolled as space expanded. In this framework, asking what happened before the Big Bang is like asking what lies west of the edge of a painting. It's not hidden, it simply doesn't exist. Another theory comes from string theory and M theory, which propose that our universe is one of many, a brain floating in a higher dimensional space. In some versions, the Big Bang was a collision between two brains, huge multidimensional surfaces slamming into each other, releasing energy and triggering expansion. In that case, there was a before, but it wasn't our time. It was a higher dimensional time, unrelated to the seconds and minutes we count. Our time began with the bang, but the multiverse has its own clocks. So which is it? Was the Big Bang the true beginning? Or just a doorway? Was there a timeless void, A previous universe, a higher dimensional collision? We don't know, and maybe we can't know, because whatever existed before time may be forever outside the reach of clocks, telescopes, and mathematics. But that hasn't stopped us from searching. Every improvement in cosmology, every deeper observation of the cosmic microwave background brings us closer to the first moments. We can see the universe as it was, just 80,000 years after the Big Bang, a baby, still glowing from birth. And soon, new instruments may let us peer even further, to the first seconds, the first instants, perhaps to the very horizon where time itself emerged. And if we listen closely, the universe might whisper its origin story, or it might remain silent, a mystery wrapped in light. Still, the question leaves an echo, not just in science, but in us. Because asking when time began is also asking when we began, not just humanity, but experience itself. Awareness, change, the unfolding of now. If there was no time, there was no memory, no motion, no possibility. The beginning of time is the beginning of everything. And perhaps that's why we keep returning to it. It's not just curiosity, it's a kind of longing to understand how something emerged from nothing, to know how the infinite arose from the void, to find out why the universe chose to be. Chapter 6. The Mystery of Now. What is the present moment? We live in the present, we act in the now, we remember the past, and we imagine the future. But when you stop and really think about it, you realize something strange. What is now? What defines this exact moment in time? The instant you are hearing this sentence? Is it a razor-thin line between past and future? Is it a measurable window, or is it just an illusion? In daily life, the present feels real. It's the moment we occupy, the one we're aware of. We experience life as a sequence of nows, each one fading into the past as the next arrives. But physics doesn't see it that way. There's nothing in the equations of motion, or quantum mechanics, or relativity that singles out a special now. All times past, present and future, asked equally in the math. There is no preferred moment. This leads to a radical possibility, that the present moment is not an objective feature of the universe, but a subjective experience constructed by our minds. Let's start with how long now really lasts. Neuroscientists have studied this, and what they've found is fascinating. Your experience of the present isn't instant. It's not a point, it's a short stretch of time about 2 to 3 seconds long. This is called the specious present, the window your brain uses to perceive events as happening now. It's long enough for a spoken phrase, a musical beat, or a sip of coffee. Any shorter, and events feel disconnected. Any longer, and they start to feel like memories. Everything you experience, the sound of your breathing, the warmth in your hands, the movement of light, is delayed. Signals from your eyes and ears take time to reach your brain, and your brain takes time to process them. What you think of as now actually happened a fraction of a second ago. You're always slightly behind the world, but you never notice, because your brain does something brilliant. It synchronizes inputs, it stitches them together into a seamless narrative, a unified now. Even when the signals arrive at different times, you perceive them as part of the same moment. This leads to a strange conclusion. The present is not something we observe, it's something we assemble. Our brains blend sensory data with memory and prediction to create a smooth, continuous experience of time. What you feel as now is a reconstruction, not reality, but a model of it. Let's think about light. Light from the sun takes about 8 minutes to reach Earth. So when you look at the sun, you're seeing it as it was, not as it is. The same goes for stars. Some are hundreds or thousands of light years away. You're seeing light that left them long before you were born. Even looking across a room, you're seeing the past. The very recent past. But the past, nonetheless. There is no instant connection to anything. Everything you see is delayed by distance, which means the idea of a universal now, a single shared moment, is an illusion. Einstein understood this. In special relativity, simultaneity is relative. Two observers moving at different speeds can disagree on what events happen at the same time. For someone moving near the speed of light, your present could be their past, or their future. There's no absolute now, only sequences that depend on motion. This idea was famously illustrated in a thought experiment. Imagine a train passing by. Two lightning bolts strike the front and back of the train at the same time from the perspective of a person standing on the platform. But for someone riding inside the train, moving toward one bolt and away from the other, the strikes appear to happen at different times. Each observer is correct, from their own frame of reference. There is no single moment where all observers agree on what now means. This destroys the idea of a global present. Instead, we each experience our own slice of time, our own personal now, based on where we are and how we're moving. The present becomes local, subjective, fragmented, and yet, we treat it as real. We build our lives around it. So where does that leave us? Some physicists have proposed a solution, a new way to think about time that doesn't rely on the present as a fixed boundary. One idea is the block universe. In this model, time is a dimension. Just like space, all events, past, present, and future, exist together, laid out in a four-dimensional structure called spacetime. You don't travel through it, you just experience different slices of it, like reading pages in a book. What we call now is simply the page we're on, but the other pages, the past and the future, are still there. They haven't disappeared or failed to exist. We just aren't experiencing them in this moment. This view can be unsettling. If the future already exists, do we have free will? Are our choices real or already written? That's still debated. Some argue that consciousness moves through the block, selecting one path among many. Others suggest that all paths exist, and we only feel as though we're choosing. But either way, the present becomes less special. It's not the center of the universe, just one coordinate on the map. Still, from the perspective of lived experience, now is everything. You don't live in the past. You don't live in the future. You only ever live in this moment. And this moment is always changing. So while physics may not recognize the present as special, our minds do. Our emotions, our memories, our sense of identity, they all revolve around the present. We feel joy now. We suffer now. We wonder now. Even our regrets and hopes only exist in the context of the current moment. So perhaps the mystery of the present is not just about physics, it's about consciousness. Your brain creates a feeling of now. It gives you a center, a point of reference. Without it, your thoughts would scatter. Your memories would lose shape. You'd float in chaos, but with it, you feel grounded, alive, aware. And that sense of now may be the closest thing we ever get to touching time itself. Some neuroscientists have even suggested that the feeling of now is what creates time, that our sense of flow, of change, of movement from one moment to the next, is a construction, a trick of perception. In that case, time isn't a feature of the universe, it's a feature of the mind, and the present moment, the now you feel so deeply, may not be real in a physical sense, but it is real to you. And that might be enough. But if now is subjective, if it's a mental model, what happens when consciousness changes? Under the influence of certain drugs, during meditation, or in altered states, people report strange experiences of time. Moments stretch, minutes become hours, hours collapse into seconds, sometimes time seems to stop altogether. What's happening in these states is not a change in the outside world, but a shift in the way the brain constructs now. The sense of the present can be expanded or dissolved, and that reveals just how fragile it is. We walk through life feeling like the present is a stable platform, but really, it's a moving window, built moment by moment from perception and memory. And in that window, we tell the story of our lives. Each thought, each breath, each heartbeat is part of the unfolding now. And maybe that's the only now that matters. Not the cosmic now, not the mathematical now, but the human now. The moment we feel, the moment we love, the moment we choose, that fleeting, fragile instant where the past ends and the future hasn't yet begun. Chapter 7. Biological Time. The clock's inside us. You have a clock inside you, not a ticking machine made of gears and hands, but a living system, quietly counting the rhythm of life. It's in your cells, your brain, your breath, your heartbeat. Even when you ignore the outside world, no sunlight, no schedules, no alarms, your body still keeps time. This is biological time, and without it, nothing in your body would work. Your body doesn't just exist in time, it depends on it. Every process inside you is timed. Your sleep, your hunger, your hormone levels, your energy, your focus, your body temperature. These fluctuations follow rhythms, cycles that repeat, patterns that give structure to your biology. The most important of these rhythms is your circadian rhythm, a cycle of roughly 24 hours that governs when you feel awake, when you feel tired, and when your body does its silent work. Circadian comes from Latin, circadian. It means about a day. This rhythm is hardwired. Even if you live in total darkness, your body still runs on a 24-hour cycle. That rhythm is controlled by a part of the brain called the suprachiasmatic nucleus, a tiny cluster of cells in the hypothalamus, just above where your optic nerves cross. This cluster, only about 20,000 neurons, acts as your master clock. It receives signals from the eyes, detecting light and dark, and uses that information to synchronize your internal processes. When light hits your eyes in the morning, the clock tells your body to reduce melatonin, the hormone that makes you sleepy. In the evening, as light fades, melatonin rises again. This daily dance tells you when to wake and when to sleep. But that's just the beginning. Your body contains peripheral clocks too, in your liver, your muscles, your heart, your pancreas, your skin. These clocks are like instruments in an orchestra, each with its own rhythm, but all tuned to the conductor in your brain. When the system is synchronized, you feel alert during the day, sleepy at night, hungry at regular times, and your body heals, digests, and recovers with smooth precision. But when the clocks are out of sync, when you cross time zones, stay up too late, or ignore natural light, you feel it. Jet lag, fatigue, fog, mood shifts. Your body is trying to recalibrate, to find its rhythm again. And this rhythm doesn't just affect how you feel, it influences your health. Disrupting your circadian cycle has been linked to heart disease, obesity, diabetes, and even some forms of cancer. Night shift workers, for example, face higher risks of chronic illness, not just because of stress, but because their biological time is constantly battling environmental time. When your internal and external clocks are misaligned, your system loses harmony. But beyond the 24-hour cycle, there are other biological rhythms too. Your body operates on ultradian rhythms, shorter cycles that occur throughout the day. These include your sleep stages, appetite waves, and periods of alertness. One common ultradian rhythm is the basic rest-activity cycle, which governs bursts of focus and energy that typically last 90 to 20 minutes. That's why your attention ebbs and flows. You feel sharp, then drift, then refocus. Even while awake, you oscillate, rising and falling with hidden waves of brain chemistry. There are infradian rhythms as well, longer cycles like the menstrual cycle. These govern not just fertility but mood, temperature, metabolism, and more. And in animals, infradian rhythms drive hibernation, migration, and reproduction. Even in humans, longer cycles exist, seasonal patterns, yearly rhythms, that scientists are only beginning to understand. Why do some people feel sluggish in winter? Why do illnesses flare with the seasons? The answers may lie in rhythms we don't yet fully grasp. And then there's your aging clock, the slowest rhythm of all, a long, irreversible march from birth to death. Every cell in your body carries a biological time stamped in your DNA, in your telomeres, in your gene expression. Scientists now believe you can estimate a person's biological age by analyzing markers in their cells, a number that might differ from their actual chronological age. Some people age faster, others more slowly, and this biological clock may be influenced by sleep, diet, stress, and lifestyle. In other words, time isn't just something that happens to you, it's something your body measures and responds to. But your experience of time, how long things feel, can also be shaped by biology. Your dopamine system, which governs reward and motivation, affects time perception. When dopamine is high, time feels fast. When it's low, time drags. This is why enjoyable experiences fly by, and boring tasks feel endless. And in people with certain conditions like Parkinson's or ADHD, Dopamine imbalances can distort time perception even more. They may struggle to estimate how long something takes, or feel like time is slipping through their fingers. Stress also bends your sense of time. When you're anxious, your body goes into survival mode. Your heart rate rises, your senses sharpen, you become hyper-aware. In this heightened state, your brain takes in more information per second, which can make moments feel longer. This is why people often report that time slows down during accidents or traumatic events. It's not that time itself changed, it's that your memory of the moment became more detailed. And those details make the moment feel stretched. Sleep is another time shaper. During sleep, your brain doesn't experience time normally. You might dream for what feels like hours, but wake to find only minutes have passed. Dream time is subjective, non-linear, strange, and it suggests that your sense of time isn't tied to the outside world. It's built internally, by your state of consciousness. Some people have a rare condition called chronesthesia, a heightened awareness of the past and future. They can mentally travel through time, revisiting memories, imagining possibilities with vivid detail. And it turns out, this ability is tied to specific brain regions: the prefrontal cortex, the hippocampus, the default mode network. These areas are active, not just when remembering the past, but when imagining the future. To your brain, memory and imagination are deeply connected. Both involve building models of moments that aren't happening now. In that sense, your brain is a time machine, constantly simulating past experiences and future outcomes. This capacity for mental time travel may be uniquely human. It allows you to plan, to regret, to hope, but it also burdens you. You relive mistakes, you fear outcomes, you worry about time running out. No other animal does this, at least not like we do. Our awareness of time is both a gift and a weight. Still, biology offers tools, ways to align with time, rather than fight it. Exposure to natural light resets your circadian rhythm. Regular sleep strengthens your internal clock. Meditation slows your perception of time. Breathing deeply stretches the present. By tuning into your body's rhythms, you can soften your relationship with time. You can stop chasing it and start dancing with it. Because time isn't just out there, in space, in stars, in equations. It's inside you, pulsing through your cells, guiding your thoughts, telling your body when to wake, when to rest, when to grow. And even as the years pass, as your body changes, as memories fade, those rhythms remain. A quiet clockwork beating beneath your awareness. Chapter 8. Animal Time. How other species perceive the clock. We live by the clock. Hours, minutes, seconds, scheduled, measured, and tracked. But what about animals? Do they feel time the same way we do? Do they know what now means? Or how long a minute lasts? In truth, every species lives in its own rhythm, its own version of time, shaped by biology, environment, and evolution. Some animals experience time slowly, noticing details we miss. Others let it rush past them, living in blinks and bursts, and studying them helps us see how elastic and strange time truly is. Let's start with one of the simplest questions. How fast do animals perceive time? To answer this, scientists use a concept called critical flicker fusion frequency. It's a way to measure how quickly an animal's brain can process visual information. Imagine a blinking light. If it blinks slowly, you see each flash. If it blinks faster and faster, at some point it stops appearing as a flicker and becomes a steady glow. The speed at which this change happens reveals how quickly your brain updates what you see. For humans, this threshold is around 60 flashes per second. But for some animals, it's much higher. Flies, for example, can detect flickers at over 250 times per second. That means their brains process visual scenes 4 to 5 times faster than ours. To a fly, your hand moving to swat it feels like slow motion. It has more time from its perspective to react, dodge, escape. This isn't magic, it's perception. Time moves faster because the fly's brain samples reality more often. Other fast-seeing creatures include birds, especially small, agile ones like hummingbirds or pigeons. They need quick visual updates to fly through dense forests, catch insects mid-air, or land precisely on tiny branches. For them, A single second contains far more information than it does for us. Their time is rich, dense, detailed. Where we see a blur, they see clarity. But not all animals move fast. Some live in slower rhythms. Elephants, for instance, process visual and auditory signals more slowly. Their flicker fusion rate is lower, and that makes sense. Large animals with long lifespans don't need rapid updates. They live in broad cycles, years, migrations, generations. They don't dart or flinch. They observe. They remember, and that memory is deeply tied to time. Elephants have extraordinary temporal awareness. They can remember the location of waterholes for decades. They recognize individuals they haven't seen in years. They mourn their dead, sometimes returning to the bones of lost companions. Their sense of time is long, spanning lifetimes, not seconds. Dogs, on the other hand, experience time in a more complex way. They don't read clocks, but they sense duration. Studies show that dogs behave differently when left alone for 30 minutes versus 2 hours. Their behavior suggests they can feel the difference. But how? It may be through smell. Scent particles fade with time, and dogs have an extraordinary sense of smell. They may gauge how long you've been gone by the intensity of your lingering scent. In that way, they build a sensory clock, not by counting seconds, but by measuring change. This brings us to an important idea. Time perception is often linked to change. The more things change around you, the more time seems to pass. This is true for humans and for animals. In stimulating environments where new sights and sounds appear constantly, time feels rich, layered, long. In dull environments where little changes, time collapses. This is why caged animals often pace or self-stimulate. Their environments lack change, and their inner time becomes distorted. Animals in the wild live by natural rhythms. Sunrise, sunset, seasons, tides, migration patterns. Some species are tuned to diurnal cycles, active by day, resting by night. Others follow nocturnal rhythms, emerging under moonlight, and some follow crepuscular time, active at dawn and dusk. These rhythms are not just habits, they're embedded in the body, in hormone cycles, brain activity, temperature. Even simple organisms like fruit flies have circadian clocks. Some species go further. Take the Arctic ground squirrel. It hibernates for up to 8 months, its body temperature dropping below freezing, its heart slowing to just a few beats per minute. During that time, its brain shuts down most functions, including time perception. To the squirrel, hibernation is not a long stretch of bored digits. Nothing. Time doesn't pass. It just disappears, and then as spring returns, so does the clock. Then there's the desert-dwelling spadefoot toad. It lives underground for years, waiting for rare rains. When the water comes, it emerges, breeds, feeds, and returns to the sand. To us, it seems frozen in time. But for the toad, its timing is perfect, tuned to cycles longer than a human memory. Evolution has taught it when to be still and when to act. Other creatures, like salmon, return to the rivers where they were born, years after they left, navigating thousands of miles through oceans and currents, back to a precise location. Their internal clocks aren't just circadian, they're annual, perhaps even biodecadal. They measure time not in hours, but in life stages. And then we come to animals, with extraordinarily short lives. The mayfly, for example, spends most of its life underwater as a nymph. When it finally emerges as an adult, it lives only a few hours, just long enough to reproduce. To us, that seems tragic. But from the mayfly's perspective, that short span may feel full. Its time is not measured by our clocks. It is measured by instinct, motion, completion. Even insects like bees show remarkable temporal intelligence. Bees can learn to associate certain flowers with specific times of day. They return at the same hour, anticipating when nectar will be available. This suggests they don't just react to time, they predict it. They live in a world of patterns, and they learn the rhythm. Birds, too, have internal calendars. Some species begin migrating, even if kept in artificial environments, with no seasonal cues. They feel the time in their biology, and some migratory birds even adjust their sleep patterns mid-flight. napping with one brain hemisphere at a time so they can stay aloft for days or weeks. To them, time is altitude, direction, wind. They don't need clocks. They are clocks. So what do we learn from all this? That time is not a single experience. It's a spectrum shaped by size, speed, senses, and lifespan. A hummingbird's second is not the same as a whale's. A mouse's hour is not an elephant's. Each creature lives inside a biological frame rate, a tempo of perception and response, and those frames define their world. Even in humans, our sense of time changes with age. Children experience time as slower, because their brains are absorbing more novelty. New experiences stretch the moment. Everything is vivid. As we age, routine compresses time. Days blend. Weeks blur. Our frame rate slows, not biologically but perceptually. And that means, in a way, we can learn from animals. By noticing, by tuning into the details, by breaking routine. We can stretch time, not physically, but emotionally. We can experience more life in the same number of minutes, because time, it seems, is not just a clock. It's attention, it's change, it's memory. To a dog, a scent is a timestamp. To a bird, a current is a schedule. To a fly, a blink is an eternity. And to us, time is whatever we choose to notice. So maybe there's no right way to live in time. Maybe we're all just moving at different rhythms, through the same silent dimension. Some fast, some slow, some brief, some long. But all of us, right on time. And now we return to ourselves, not as animals, but as minds, to explore the psychological flow of time, and why it speeds up, slows down, or even disappears altogether, depending on what we feel. Chapter 9: Psychological Time. Why moments stretch or vanish. There are days when time flies past us, as if it has wings. Other days feel like a slow crawl through molasses. Every minute a wait, every hour a long inhale that never quite exhales. We speak of time speeding up, slowing down, getting lost, or dragging on, but the clocks on the wall don't change. The second hand still ticks in perfect rhythm. So what exactly changes when we feel time shifting beneath our feet? This is the mystery of psychological time, the way your mind constructs the flow of moments, not through physics, but through perception. Time, in the physical sense, may be measured in seconds and hours, but your lived experience of time is measured in attention, memory, and emotion. The brain doesn't simply record what happens. It interprets, prioritizes, and edits. And in that editing, time bends. Sometimes without warning, often without logic. Your mind is not a passive witness. It is the author of your experience of time. When you focus intensely on a task, you often lose track of time. You begin writing, or painting, or coding, and look up hours later, surprised by the dark. This state, known as flow, compresses time. Your brain enters a state of deep engagement, minimizing distractions, reducing your internal clock's awareness of each passing second. The passage of time becomes irrelevant, because your attention is fully absorbed in the present activity. In this state, memory creation slows down, so when you look back later, there are fewer reference points to fill the space. It feels as if less time has passed, even though the clock says otherwise. By contrast, moments of boredom or discomfort expand time dramatically. Waiting in line, sitting in traffic, or enduring a dull lecture can make 5 minutes feel like an eternity. When your brain lacks stimulation, it begins to scan for novelty. With little to focus on, your internal clock pays more attention to itself. Time becomes the experience. And when you're watching the seconds tick by, each one feels longer. That same mechanism is at work during pain, sadness, and anxiety. When you are uncomfortable, your brain becomes hyper-vigilant, your awareness sharpens, and time slows to a crawl. But the most dramatic time shifts happen during moments of crisis. People who have experienced accidents, near-death events, or sudden trauma often report that time slowed down, or even stopped. The world becomes detailed, almost cinematic. Colors seem more vivid, thoughts feel fast and clear. This effect isn't just storytelling, it's the brain's survival mechanism. Your stress response floods your system with adrenaline, speeding up memory encoding and boosting perception. Because you're processing more information per second, your retrospective memory is packed with detail. When you recall the moment later, those dense memories make the event feel longer than it actually was. Strangely, the opposite can also happen. Under extreme trauma, time can vanish. Some people report that hours go missing. They remember only fragments or nothing at all. In these cases, the brain protects itself by fragmenting consciousness. When emotion overwhelms perception, memory encoding may shut down entirely. The result is a blank space in the timeline, a pocket of lost time. Our perception of time is also shaped by familiarity. When you experience something new, your brain pays closer attention. It creates fresh memories, builds novel connections, and catalogues sensory detail. This makes the experience feel longer. It's rich with markers. But when you follow a routine, commute the same road, eat the same lunch, repeat the same conversation, your brain skips the fine details. It compresses the event, files it away as familiar, and so time feels shorter in hindsight. This is one reason why childhood feels so long and adulthood feels like a blur. As children, every experience is new. New sights, new words, new emotions. Our brains are in constant learning mode, so each day is filled with high-resolution memory. As adults, life becomes repetitive. We settle into patterns. We move through the day on autopilot. When we look back, there are fewer memory anchors, and the time collapses. Years feel like months. Months feel like weeks. This illusion becomes more noticeable as we grow older. It's not that time speeds up, but that our perception of time compresses due to repetition and reduced novelty. Some psychologists call this the proportional theory. Each year you live becomes a smaller percentage of your life. To a 5-year-old, 1 year is 20% of their memory. To a 50-year-old, it's only 2%. So it feels shorter, not because it is, but because of how much space it occupies in your story. Emotions also color the passage of time. Happiness can stretch or shrink time, depending on context. Joyful moments often feel fast while they're happening, but long when remembered. This is because your brain encodes more detail when you're emotionally engaged. Later, those memories play back with rich context, giving the illusion of extended time. On the other hand, fear, grief, and loneliness can warp time in unpredictable ways. Grief can stall the sense of flow completely. Days blur into each other. Clocks feel irrelevant. Time becomes heavy. Not because it drags, but because it loses meaning. Mental health conditions also affect temporal perception. In depression, time often feels slowed and flattened. Hours pass with little variation. Days feel identical. This may be due to reduced dopamine activity, which blunts emotional highs and lows, and dampens time sensitivity. In anxiety, time often feels sped up, but fragmented. You rush from task to task, rarely feeling present. The mind anticipates future threats, but fails to settle in the now. Even disorders like schizophrenia can distort time. Some patients report hearing voices that don't fit the normal rhythm of speech. Others feel disconnected from the flow of time entirely, as if stuck in a different dimension. These altered perceptions highlight how tightly time is woven into our sense of self, and how easily it can unravel when the brain's internal clock misfires. Drugs can also bend time dramatically. Stimulants may accelerate it, psychedelics may stretch it, depressants may erase it. Under the influence of LSD, users often report that seconds feel like hours, or that they lose the ability to track time altogether. This is because these substances affect the brain's default mode network, the system responsible for narrative, memory, and self-awareness. When that system is disrupted, your sense of time detaches from the usual markers. Moments expand, contract, or loop. The arrow of time feels more like a circle. But not all altered time is disorienting. Meditation practices, especially those focused on breath and body awareness, can slow the perception of time while increasing present moment clarity. Monks in deep states of mindfulness report feeling timeless, as if awareness stretches beyond the usual boundaries. This state, sometimes called eternal now, is not about escaping time, but about entering it fully. By quieting the mind's chatter, you reduce your reliance on memory and anticipation. And in doing so, you experience time not as pressure, but as presence. This reveals something profound. Time, for us, is not just a backdrop. It's a feeling, a weight, a language of change, written by the brain. You don't just move through time. You interpret it. You shape it. You live inside a timeline. You're constantly rewriting. This means we can also choose how we relate to time. When we slow down, engage with novelty, or tune into the richness of now, time expands. When we rush, avoid, or repeat, time shrinks. It's not always easy, but the awareness alone can change how we live. Because even if we can't stop time, we can shift how it feels. And perhaps that's what truly matters. Not how many minutes you live, but how fully you experience them. Not the speed of the clock, but the depth of the moment. Now, we shift from the mind to memory, to explore how the brain stores time, retrieves it, and builds the timeline we call a life. Because every moment you remember is a piece of time made permanent. Chapter 10. Memory and Time. How the brain remembers the past. Your life is made of moments. Some vivid, some faint, some buried, so deep they feel like dreams, and all of them stored in the quiet folds of your mind. Memory is your time machine. It's how you travel backward to yesterday, to childhood, to a feeling that never quite faded. But memory doesn't just help you recall, it helps you be. Without it, there's no continuity, no sense of self, no past to reflect on, and no way to imagine what comes next. The human brain does not record life like a camera. It's not a reel of perfect footage. It's a creative editor, extracting details, discarding others, reshaping the story so it fits your sense of meaning. Every memory you hold is reconstructed when you recall it. It isn't a snapshot, it's a recreation. You remember not what happened, but how you felt when it happened, what you noticed, what mattered. The rest fades into static. Memories are formed through a process called encoding. When you experience something, a face, a sound, a conversation, your senses collect information and relay it to different brain regions. The hippocampus acts as a hub, sorting and indexing experiences so they can be stored for later. At the same time, the amygdala tags experiences with emotion. Events that trigger fear, joy, sadness, or excitement are prioritized. They burn brighter into your memory. That's why you remember where you were during important events, a graduation, a breakup, a moment of danger, but forget what you had for breakfast 3 days ago. Emotion makes memories stick. Once encoded, memories are stored across the brain in distributed networks. The sounds of a moment may be stored in auditory regions, the colors and shapes in visual areas, the feeling of touch in the somatosensory cortex. Recollection involves reactivating this web, pulling together scattered fragments and stitching them into a coherent image. But this stitching isn't always precise. Memories are fluid. Each time you recall them, they're slightly rewritten. You reinforce certain parts. You add new meaning. You may even incorporate details that never happen. This process is called reconsolidation, and it makes memory both powerful and unreliable. Still, despite their flaws, memories give you a sense of time. You don't just store events, you store when they happened, and in what order. This sense of temporal sequencing allows you to look back on your life as a timeline. It's not perfectly spaced or scaled. Some months feel compressed, some hours feel stretched. But the brain preserves relative order. What came before, what followed. This tati comes from multiple systems. Your episodic memory stores personal experiences, the time you saw snow for the first time, the day you met a friend, the sound of a voice that meant something to you. Your semantic memory stores facts and knowledge, things you learned, things you know. And your procedural memory stores skills, how to tie a shoe, how to ride a bike. Each system has its own relationship to time. Episodic memories are rich with context, time, place, emotion. They allow mental time travel. Semantic and procedural memories are timeless. You don't remember when you learned to speak, you just know how. What's remarkable is how these systems let you not only remember the past, but imagine the future. The same brain regions, used to recall old experiences, are used to construct future possibilities. You simulate outcomes, play scenarios in your mind, and test options, all using fragments of memory. Your idea of what might happen is built from what has happened. This simulation engine helps you plan, anticipate, and prepare. It gives you a sense of continuity, a self that stretches across time. You are not just who you are now, you are who you remember being, and who you expect to become. Take away memory, and that continuity shatters. That's what happens in conditions like amnesia. People who lose episodic memory often retain language and knowledge. They can speak, think, even reason, but they lose the narrative. They don't remember yesterday, and they can't imagine tomorrow. They become trapped in a perpetual now, unable to anchor themselves to time's flow. The most famous case of this was a man known as HM, who had parts of his hippocampus removed to treat seizures. After the surgery, he could remember events from early life, but could no longer form new episodic memories. He lived moment to moment, aware, intelligent, polite, but unable to remember what had just happened or what was about to happen. He would meet someone, then forget the meeting within minutes. To him, time had no continuity. Each moment stood alone, untethered. Memory shapes our identity, not just in facts and events, but in emotion. You don't just remember what happened, you remember how it made you feel, and that emotion echoes into the present. Trauma is one example. For some, painful memories don't stay in the past. They replay, re-trigger, and rewire perception. The trauma doesn't feel like something that happened. It feels like something that's still happening. Time loses its distance. The past breaks into the present. Therapies like EMDR and memory reconsolidation techniques aim to help the brain reprocess these memories, giving them a new emotional frame, placing them in the past, where they belong. Because healing, in many ways, is the ability to let time pass without dragging everything with you. Memory is powerful, but sometimes we must teach it when to let go. Not all memory is about trauma. Some is about beauty. The taste of a favorite dish, the smell of a loved one's clothes, a melody that takes you back to a specific hour, a single sunset. These sensory fragments anchor moments in time. Your brain links smell, sound, and sensation to emotional states, creating associative memories that can last a lifetime. This is why music can transport you instantly. A few notes can open a doorway, a portal to a place that no longer exists, but still lives inside your mind. Memory also influences time perception. As you live through an experience, you may feel it passes quickly, but when you remember it later, if it's rich in sensory and emotional detail, it feels longer. The more memory you create during an experience, the longer it seems in retrospect. This is why novelty expands time. A week spent exploring a new city feels longer in memory than a week doing routine work, because each new experience adds texture to the timeline. This suggests something important. You can shape your sense of time by choosing how you live. More novelty, more awareness, more attention. These things slow time down, not in reality, but in memory. And because memory is how we construct the past, they make life feel fuller, not longer in length, but deeper in substance. Even forgetting serves a purpose. The brain forgets to save space to prevent overload, to filter noise. You remember what's useful, what's meaningful, what builds the story of you. But forgetting also makes room for growth. Letting go of outdated memories allows new perspectives to take root. Memory is not a static archive. It's a living system, malleable, adaptive, sometimes fragile, but endlessly creative. And it is, in many ways, the interface between your consciousness and the fourth dimension. You don't move through time like a train on a track. You move like a weaver, threading moments into meaning, linking now to then, and shaping tomorrow with what you remember. When you tell someone who you are, you tell them a story. That story is memory, and that memory is time, compressed into identity. You are a collection of yesterdays, woven into a single voice, and every time you recall a moment, you become it again, if only for an instant. Now, we leave the past behind and step out of the mind into the machines we've built to master time. Clocks, calendars, precision. Because for all our questions about time's nature, we've spent thousands of years trying to measure it. And every tool we made reflects how deeply time shapes civilization. Chapter 11. Measuring time. From shadows to atoms. Before we understood time, we tried to track it. Before we studied it, we measured it. We noticed the sky. We watched the sun climb, the moon change, the seasons shift. Long before clocks and calendars, our ancestors were already watching time unfold, searching for patterns in the chaos of nature. And from those patterns, they began to build order. The earliest timekeeping devices weren't machines, they were shadows. As the sun moved across the sky, it cast lines across the ground, a stick in the earth, a column in a courtyard. Each one became a marker. The sundial was born, crude at first, but elegant in principle. By watching the length and direction of shadows, people could divide the day into sections, morning, noon, and night. It wasn't exact, but it was enough to plant, harvest, and gather, enough to shape ritual, commerce, and survival. But sundials had a flaw. They only worked when the sun was visible. So as civilizations advanced, they created new ways to count time. Water clocks, or klepstras, used the steady drip of liquid to track the passage of hours. These devices, used in ancient Egypt, Babylon, and China, allowed people to measure time even in darkness. The flow of water, though simple, became a powerful metaphor. Time as a stream, always moving, never stopping. Sand glasses followed, grains flowing from one chamber to another, dividing time into fixed intervals. Then came mechanical clocks in the towers of medieval Europe, driven by gears and weights. These machines ticked and tocked, not only marking the hours, but also announcing them with bells, chimes, and movement. For the first time, people could coordinate across distance. They could agree on when to pray, when to trade, when to meet. Time became public, shared, structured. With each improvement in timekeeping, our relationship to time changed. It became tighter, sharper, more demanding. As clocks grew more precise, so did expectations. Arrive on time, work by the hour, bill by the minute. Time transformed from a flow into a grid. In the 17th century, the invention of the pendulum clock revolutionized accuracy. Galileo had observed that a swinging pendulum keeps a steady rhythm, and this idea was refined by Christian Huygens, who built the first reliable pendulum timepiece. Now clocks could measure seconds precisely, a concept that barely existed before. This leap wasn't just technical, it changed how people thought. A second wasn't just a blink, it was a unit, a standard. Later, the spring-driven pocket watch made time portable, no longer tied to towers or walls. People could carry time with them. This changed everything. Merchants, travelers, officers, scientists, all could align their actions, not with the sun, but with the tick of a mechanism. The world began to sync, not to nature, but to engineering. But as we explored further, across continents, through oceans, we discovered another challenge. Different cities used different clocks. Noon in one place was not noon in another. This wasn't a problem until trains arrived. Railways demanded coordination, schedules, safety. So in the 19th century, governments introduced standard time zones. Now vast regions shared a common clock. Greenwich Mean Time became a reference, a 0 point on the world's temporal map. And suddenly, time was not just personal or local, it was global. Still, we wanted more precision. In the 20th century, as science demanded greater accuracy, we turned to the quantum world. Atomic clocks were born. These devices don't rely on pendulums or gears. They measure the vibrations of atoms. Specifically, cesium-33. A cesium atom, when exposed to certain energy, vibrates at a consistent frequency. 9,001 to 2,631,007 to 70 cycles per second. This became the new definition of a second, not based on Earth's rotation, but on the ticking of nature's smallest building blocks. With atomic time, our accuracy jumped from seconds to nanoseconds. GPS satellites, stock markets, data networks, all rely on these ultra-precise clocks. Even a tiny drift can cause navigation errors, communication failures, economic losses. In this age, time isn't just measured, it's managed with surgical precision. But the deeper we look, the stranger time becomes. Atomic clocks revealed something unexpected. Einstein was right. When two identical atomic clocks are placed at different altitudes or speeds, they tick differently. A clock on a plane runs slower than one on the ground. A clock on a satellite runs faster than one on Earth. This isn't theory anymore. It's measurable. Every time we synchronize satellites, we account for relativity. Time is not constant. It bends, and our machines bend with it. Today, the most precise timekeepers on Earth are optical lattice clocks. They trap atoms in laser grids and measure their oscillations with staggering accuracy. These clocks are so precise they would lose less than 1 second over the age of the universe. They are not just tools, they are portals into the deep structure of spacetime. They help us test the limits of physics, search for tiny variations in gravity, and probe the foundations of reality. But even as we master the measurement of time, the mystery remains. What exactly are we measuring? A flow? A change? A sequence of states? We use clocks because we can't grasp time directly. We measure what changes, not what time is. Calendars add another layer to this story. Long before clocks, humans built complex systems to track the passage of months and years. The lunar calendar followed moon phases. The solar calendar followed the sun's position. The lunar-solar calendar blended both. These systems were used not just for agriculture, but for religion, law, and culture. Festivals, rituals, taxes, all tied to celestial rhythms. Our oldest monuments, like Stonehenge or the pyramids, are aligned with solstices and equinoxes. These were calendars carved into stone. Even today, we live by layered time. A Gregorian calendar, a 7-day week, a 24-hour clock, a 60-minute hour. All of these are inventions, agreed upon, codified. They help us coordinate, but they also shape our experience. We think in days and weeks because we've built our lives around those units. But they are not natural. They are frameworks, ways to make sense of the infinite. Without these tools, time feels slippery. We forget how long things take. We underestimate deadlines. We lose our place. Clocks and calendars ground us. They provide orientation, but they also trap us. We feel pressure from time, urgency, scarcity, aging. We chase the clock, even when there's no reason to run. So maybe the question is not how to measure time better, but how to live with it more wisely. Precision has its place. Science needs it. Systems depend on it. But as individuals, we also need softness, the ability to breathe inside time, not just count it. Some cultures move slower. They prioritize presence over punctuality. They value cycles over deadlines. Others run fast. Fast meals, fast meetings, fast lives. But no matter how you measure time, you live it one moment at a time, and no clock can measure what a single moment truly means. From shadow to sundial, from water to wheels, from quartz to cesium, from atoms to photons, we've refined the art of tracking time. We've drawn lines across the sky, marked every tick, and synchronized the world. But for all our cleverness, we are still humans, trying to hold something that never stays still. And now, we turn outward, to the cosmos, to ask how time behaves, not just on Earth, but across the stars. Because in the vast scale of the universe, time reveals even deeper mysteries. Chapter 12. Cosmic Time, the Clock of the Universe. Look up at the night sky and you're not just seeing stars, you're seeing the past. Light takes time to travel. The farther you look, the older the light becomes. That star twinkling overhead may no longer exist. Its light began its journey before your grandparents were born. You are not looking at what is. You are looking at what was. And this delay, this cosmic echo is not a glitch. It's a feature of reality. It's how we measure time on the largest scale imaginable. In everyday life, time feels local. You wake up, you eat, you work, you rest. Time moves with you. But in the universe, time is written across the fabric of space itself. It's not a rhythm you carry, it's a pattern the cosmos weaves. And to see it clearly, we have to look far. Because the deeper we peer into space, the further back in time we go. This idea forms the basis of cosmic time, a way of understanding the age and evolution of the universe, from its earliest moments to now. Cosmic time doesn't depend on your clock, your planet, or your body. It begins with a single origin point, the Big Bang. That event, or whatever the true beginning was, marks time zero. Everything since has been unfolding outward, driven by energy, gravity, and expansion. From that reference point, we say the universe is about 13.8 billion years old. That number isn't just guessed. It's calculated from data from the cosmic microwave background, the motion of galaxies, and the ratios of ancient elements. But what does it mean to say the universe is 13.8 billion years old? Where is that clock ticking? In cosmology, time is measured by imagining a kind of ideal observer, one who floats in empty space, unmoving, unaffected by local distortions. From that vantage point, we count cosmic time as the age of the universe since expansion began. But in other parts of the universe, time may pass differently. Near black holes, in early galaxies, in regions of intense gravity, the passage of time stretches or compresses, depending on conditions. So the age of the universe is a kind of average, a shared narrative we use to make sense of cosmic history. As the universe expands, space itself stretches, galaxies move apart, not because they are flying through space, but because space is growing between them. This expansion affects time. Light from distant galaxies doesn't just take time to reach us. It also gets stretched by the expanding fabric of the universe. This is called redshift. The wavelength of light increases, its frequency slows, and its energy decreases. What was once blue and bright arrives as red and faint. That shift is a measure of time, as well as distance. By measuring redshift, astronomers can determine how far away a galaxy is and how long its light has been traveling. In this way, light becomes a timestamp, a cosmic postmark from billions of years ago. And then there is the cosmic microwave background, the oldest light we can see. It's not the light from stars, it's older than that. It comes from a time when the universe was only 380,000 years old, when atoms first formed, and light could travel freely for the first time. This light, stretched by billions of years of expansion, now glows faintly in all directions. It carries the imprint of the infant universe. By studying it, we decode time's earliest chapters, how matter clumped, how space cooled, how the seeds of galaxies were sown. Cosmic time also reveals that the universe has gone through different ages. There was the radiation era, when energy dominated. Then, the matter era, when galaxies and stars took shape. And now, we live in the dark energy era, a period in which a mysterious force is accelerating the expansion of space. This acceleration means galaxies are moving away faster and faster. Eventually, some will vanish from view altogether. Their light stretched so far we will never see it. The visible universe will shrink, not because it's getting smaller, but because time and space are moving too quickly for light to keep up. This raises strange questions. If we can't see a galaxy, does it still exist for us? If its light can never reach us, can we say it shares our time? In cosmic terms, connection defines experience. If light can't bridge the gap, neither can information. And so, over cosmic time, the universe becomes increasingly lonely. Galaxies recede. Stars die. New stars form less frequently. Entropy rises. Eventually, trillions of years from now, stars will go out, black holes will evaporate, and the universe will settle into darkness, a state called heat death, when all energy is evenly spread, and nothing new can happen. Time continues, but change stops. This isn't poetic melancholy. It's the physics of a universe governed by thermodynamics. Time doesn't require movement. It only requires possibility. But when all possibilities are exhausted, when the last flicker of usable energy fades, time becomes silent, not stopped, just unmarked. An endless plain, with nothing left to measure. But that's the distant future. Right now, we still live in a vibrant, dynamic cosmos. Stars are being born. Galaxies collide and merge. Time unfolds with visible drama. And from our small corner of space, we've built tools to measure that unfolding. Telescopes act as time machines, collecting ancient photons and decoding their messages. With them, we reconstruct the past, chart the present, and predict the future. Cosmic time, though vast, is not unreachable. And in this vastness, our perspective shifts. A human life measured in decades is a blip. Civilizations rise and fall in the time it takes a photon to cross a fraction of a galaxy. Our clocks and calendars are local conveniences, designed for but the universe moves to a different rhythm, one measured in eons, in stellar life cycles, in the fusion of hydrogen, in the cooling of space. And yet, this massive scale does not diminish us. It clarifies us. To understand cosmic time is to understand how improbable it is that they are here at all. It took billions of years for stars to form, to create carbon, to scatter heavy elements through supernovae. It took planetary systems, water, cells, consciousness. And now, a small group of organisms on a rocky planet orbits a middle-aged star and thinks about time. We are the universe measuring itself, and perhaps that is the most beautiful result of cosmic time, that it leads back to awareness, that after all the light years, all the collisions, all the cooling and expanding, something arose that could look at the sky and ask how long it has been shining. We may never reach the edge of time, but in measuring it, in imagining it, we make it real to us. Cosmic time is not just a number. It's a story, written in stars, etched in light, unfolding quietly across an endless night. And now, we shrink the scale once more, from stars to seconds, to explore how time behaves in the most extreme environments we've ever imagined. Black holes, singularities, and the places where time nearly stopped. Chapter 13. Black holes and the edge of time. There are places in the universe where time almost stands still, where gravity is so intense that space itself folds in on itself and time bends beyond recognition. These are the black holes, dark, mysterious regions where matter collapses and the rules of physics blur. To understand time near a black hole is to glimpse the edge of what time can be. It's not just slower, it's distorted, twisted, and nearly frozen. The black hole begins with collapse. A star, many times larger than our sun, burns through its fuel. Without the pressure of nuclear reactions to push outward, gravity takes over. The core collapses inward, under its own immense weight, and in a fraction of a second, a singularity is born, a point of infinite density. Surrounding this singularity is the event horizon, the boundary beyond which nothing, not even light, can escape. To cross this horizon is to exit the visible universe. From the outside, it appears as a perfect void, black, silent, final. But time does not behave normally here. As you approach a black hole, gravity increases, and with that gravity comes time dilation. According to Einstein's general relativity, the stronger the gravitational field, the slower time moves, relative to a distant observer. Imagine floating near the event horizon of a supermassive black hole. From your perspective, everything feels normal. Your heart beats, your clock ticks, moments pass, but to someone watching from afar, your clock appears to slow down. They see your movement stretch, your signals redshift, you begin to freeze in time. If you hover just above the event horizon, your time slows so much that minutes for you could mean centuries for someone outside. This isn't a trick of perception, it's built into space-time. Near a black hole, time itself stretches. The deeper you go, the more pronounced the effect becomes. And once you cross the horizon, from the outside's point of view, you vanish. Not just in space, but in time. You are no longer part of their future, but from your own frame of reference. Crossing the event horizon feels ordinary. There is no wall, no sudden jolt. You fall smoothly inward. You continue to experience time in your own internal rhythm. But there is no going back. No message can escape. No signal can return. The arrow of time continues, but only for you. From the outside universe, you're frozen at the edge, suspended, never quite falling through. This leads to strange paradoxes. If someone falls into a black hole and we watch from a distance, we never see them cross the horizon. We see them approach it more and more slowly. their image red shifting into darkness. Do they fall in? Or do they remain forever stretched on the edge of existence? According to relativity, they cross the horizon. But according to our perspective, they are forever just about. It's a matter of frames, of what time means, depending on where you stand. And then there is the singularity itself. Inside the black hole, all paths lead to a single point, the core. Once you're inside, you cannot avoid it. You cannot orbit it. You cannot escape it. You are drawn in, inevitably. And near this point, our understanding of time breaks down. The equations of relativity cease to make sense. They diverge. They return infinite answers. We reach the edge of knowledge, not just about space, but about time. Some physicists believe that near the singularity, time and space may trade roles. What was once your future becomes a direction in space, and what was once space becomes time. This is more than a mathematical curiosity. It suggests that time itself is not an absolute axis. It can rotate, it can merge, it can end. Inside a black hole, your future leads you inward, always inward, toward a moment that cannot be escaped. This concept is so extreme that many believe singularities aren't real physical objects, but signs that our theories are incomplete. A full theory of quantum gravity might resolve the singularity, replacing the infinite point with a quantum description of space-time. But we don't yet have that theory, and so the heart of the black hole remains hid, a region where space collapses, time warps, and cause and effect may lose their meaning. Some researchers propose that black holes might not be the end of time, but the beginning of something else. There are speculative models suggesting that inside certain black holes, new universes could be born. The singularity, rather than a destructive core, could act as a bounce, a transition to expansion. In this view, our own Big Bang might have originated from the core of a black hole in a parent universe. It's a bold idea, with little observational evidence, but one that links the smallest and largest questions about time's origin. And black holes also reveal another problem, the information paradox. According to quantum mechanics, information cannot be destroyed. Every particle, every state, must be recoverable, even if it changes form. But black holes seem to violate this. Anything that falls and appears to be erased. So where does the information go? Does it vanish at the singularity? Does it escape somehow? Does it remain encoded on the surface of the event horizon? This last idea, the holographic principle, suggests that all the information inside a black hole might be stored on its boundary, in a two-dimensional code that describes a three-dimensional volume. If this is true, it challenges our idea of what space and time really are. Perhaps the universe itself is a hologram, with time emerging, not from depth, but from information flow. In such a model, black holes are not just astrophysical oddities, they are the keys to understanding time at the deepest level. And yet, for all their complexity, black holes are real. We have photographed one. In 2019, the Event Horizon Telescope captured the shadow of a supermassive black hole in galaxy M87. It was a circle of darkness, surrounded by glowing gas, a direct image of the point where time slows nearly to a halt. And that image, assembled from telescopes around the world, was not just a scientific achievement, it was a portrait of time on the edge of meaning. Black holes are not rare. They exist at the centers of galaxies. They form when stars die. They may even exist in miniature, created in the early universe. And wherever they are, they sculpt time around them. They show us what happens when mass and gravity push time to its limits. They remind us that time is not a passive dimension. It bends. It flows differently in different places. And under extreme conditions it can be twisted into forms we're only beginning to imagine. Black holes are both endings and beginnings. They mark the boundaries of what we can observe. They challenge the laws we thought were solid, and they invite us to rethink time, not as a uniform thread, but as a malleable substance, a thing that can be pulled, compressed, and even stopped. Next, we leave the extremes of gravity and enter the paradoxes of logic, to explore the idea of time travel, and whether the past and future are truly as closed off as they seem. Chapter 14. The Science of Time Travel. Possibility, Paradox, and Physics. Is time travel possible? It's a question asked for centuries, in myths, in novels, in films, a dream of returning to the past, or glimpsing what's yet to come. But beyond fantasy, there's a deeper question: does the universe allow it? Could the laws of physics, as we understand them, permit time travel, at least in theory? And if they could, what would that really mean? To begin, we must define what time travel is. In one sense, we are all time travelers, moving from present to future, second by second. But what we usually mean is moving against the grain of time backward, to change something, or forward, to witness something, long after we should be gone. And here, things become stranger, because modern physics doesn't forbid all forms of time travel. In fact, it predicts some. Start with Einstein's theory of special relativity. It tells us that time is not absolute. It flows differently depending on speed. As an object moves closer to the speed of light, its experience of time slows down relative to a stationary observer. This has been confirmed with atomic clocks on fast-moving jets and with astronauts in orbit. The effect is tiny at human speeds, but profound at relativistic ones. If you traveled at near light speed for what felt like a few years to you, you might return to Earth to find centuries had passed. This is one-way time travel to the future. But can we go backward? That's where things get complicated. One possible pathway comes from general relativity, Einstein's theory of gravity. It allows for the bending of spacetime by mass and energy, and under certain solutions, it permits the existence of structures called closed time-like curves. These are paths through spacetime that loop back on themselves, where an object could, in theory, return to its own past. One example is the Tipler cylinder, a hypothetical, infinitely long rotating cylinder that warps spacetime enough to allow time loops. Another comes from the idea of wormholes, shortcuts through spacetime predicted by Einstein's equations. If a wormhole could connect 2 points in time as well as space, and if one end were accelerated to create a time difference, you might, in theory, enter it and emerge in the past. But there are problems. First, we don't know if wormholes can be stabilized. They appear to require exotic matter, a substance with negative energy density, to keep them open. Such matter has never been observed in the required quantities. Second, quantum effects may destroy wormholes before anything can pass through them. Stephen Hawking proposed the chronology protection conjecture, an idea that the laws of physics prevent time travel to preserve causality. In other words, the universe might censor itself, blocking any loop that could create a paradox. And paradoxes are the heart of the problem. Consider the classic grandfather paradox. If you travel back in time and prevent your grandfather from meeting your grandmother, you would never be born. But then who went back to change it? This kind of causal loop seems logically impossible, and yet physics doesn't explicitly rule it out. Some interpretations suggest that time travel might lead to self-consistent loops, events that influence the past only in ways that preserve the future. This is called the Novikov self-consistency principle. Under this view, you could go back in time, but you could not change it in any way that would create a contradiction. Imagine dropping a billiard ball into a time machine. It emerges from the past and knocks its younger self off course, but only in a way that ensures the loop happens consistently. No contradictions, just strange feedback loops. This version of time travel is eerie, but logically stable. There's also the possibility that time travel leads to branching timelines. If you go back and change the past, perhaps you create a new reality, a parallel world where events unfold differently. This idea isn't part of standard general relativity, but it appears in quantum mechanics, particularly the many worlds interpretation. In that view, every quantum event splits the universe into multiple outcomes. So altering the past doesn't change your timeline. It creates a new one. This avoids paradox, but introduces infinite complexity. Still, even if time travel were possible, would it be usable? The energy required to create a usable wormhole may be beyond anything we can produce, and controlling the exit point in time adds another layer of difficulty. Not to mention the problem of targeting. Time doesn't just move. It happens somewhere. The Earth spins. It orbits the Sun. The Sun moves through the galaxy. The galaxy moves through space. If you return to a specific moment, but not to the same spatial coordinates, you might arrive in deep space, or inside a planet. And then there's the human factor. Would your biology survive such a jump? Could consciousness even endure rewiring of temporal causality? We simply don't know. The science is filled with possibility, but also with roadblocks. Time travel to the past remains a speculative frontier, allowed by math, but constrained by physics. Even so, it continues to inspire, not just scientists, but storytellers, because time travel isn't only about physics. It's about regret, hope, and the desire to make things right. We dream of going back to fix a mistake, to say something unsaid, to save someone. And in those dreams, we confront our limitations. Not technical ones, but human ones. The past cannot be undone. The future cannot be known. All we have is now. And maybe that's why time travel captivates us. It points to what we most want: a second chance, a glimpse ahead, a sense of control, in a universe that flows relentlessly forward. But perhaps the most powerful time travel is memory and imagination. The brain already lets us revisit the past and simulate the future. No machine required, just thought. And still, the question lingers. If a doorway through time were ever opened, would we walk through it? Would we risk the fabric of causality for the chance to rewrite fate? Or would we realize that time travel doesn't solve problems? It just moves them around. And the real challenge is learning to live in one direction with grace. Physics will continue to explore these questions. New theories may arise. Quantum gravity, string theory, loop cosmology. Each might reshape our understanding of what time even is. And in those answers, we may discover that time travel is not impossible, just misunderstood. Or maybe we're already in a loop, playing out lives written long ago, unaware of how tightly fate and free will are entangled. Or maybe not. Maybe time is a river, and we are leaves, carried forward, able only to watch as the banks drift by. Either way, the mystery of time travel is a mirror, reflecting our deepest desires and our deepest questions. Now we turn to the smallest scales where time may not even be smooth, because in the quantum world, the flow of time itself may break down. Chapter 15. Quantum time. Does time exist at the smallest scale? We've talked about time on the scale of stars, on the level of clocks, and at the edge of black holes, but now we must shrink our vision to the smallest scale known, the quantum realm. Here, time behaves differently. Or perhaps it doesn't behave at all, because when we zoom in close enough, down to particles and probabilities, we find that time itself starts to dissolve. It becomes uncertain, ill-defined, a background assumption rather than a measurable quantity. What is time when you reach the smallest units of nature? And is it possible that time at the quantum level is an illusion? In classical physics, time is absolute. It ticks forward like a metronome, unchanging, reliable, and external. In quantum mechanics, that assumption breaks down. The core of quantum theory is the wave function, a mathematical description of all the possible states a system can be in. The wave function evolves over time, governed by the Schrödinger equation. This evolution is deterministic. If you know the wave function at one moment, you can calculate it at the next. But here's the twist. This evolution happens in a time parameter that is never directly observed. Time is just a number in the equation, not a thing we measure, a backdrop. When we observe a system, its wave function appears to collapse from many possibilities to a single outcome. But that collapse doesn't occur over time. It is sudden, discontinuous. So in the quantum world, there are two kinds of time: the smooth, mathematical evolution of the wave function, and the sharp, unpredictable jump of observation. This has puzzled physicists for decades. How can the same system follow two contradictory time behaviors? What is time doing during the jump? And who, or what, decides when the jump occurs? Some interpretations of quantum mechanics try to avoid this paradox. In the many worlds interpretation, there is no collapse. All outcomes happen in branching parallel worlds. The wave function never breaks. Time flows smoothly, but that raises other questions. If all possibilities unfold, then what is the meaning of a specific moment? Is the present just one thread in a tangle of infinite timelines? And if so, why do we feel time as a single unfolding now? Then there's the problem of time in quantum gravity. When we try to combine quantum mechanics with general relativity, something strange happens. Time disappears. In the Wheeler-DeWitt equation, a proposed equation for quantum gravity, there is no time variable at all. None. It suggests that, at the most fundamental level, the universe doesn't evolve. It just is. This is called a timeless formulation of physics. Everything past, present, and future exists in a single static structure. We perceive change, not because the universe is changing, but because our experience moves through this static landscape, like a flashlight sweeping across a painting. If this is true, then time is not fundamental. It is emergent, a property that arises when many particles interact. In this view, time is like temperature. Individual atoms don't have a temperature, but a collection of them vibrating and colliding creates the sensation of heat. Maybe time is the same. No single particle experiences time. But when enough particles interact, a direction emerges. An arrow. Some researchers explore this idea using entanglement, the strange connection between quantum particles. In entangled systems, parts of the system remain correlated even when separated by distance. Time may emerge from the way these correlations evolve. In one model, known as the Page-Wouters mechanism, time arises when one part of a system acts as a clock for the rest. The total system is timeless, but from within, subsystems can experience change. This suggests that time is not a global phenomenon. It's relative, emergent, and perhaps optional. Another challenge in quantum time is the lack of a time operator. In quantum theory, we represent properties, like position, momentum, or energy, with mathematical operators. These operators act on the wave function and yield measurable results. But time has no such operator. It is not a quantum observable. We measure the outcome of a process, and we mark its duration, but time itself is not measured directly. It's a label, a scaffold, not a thing. And that distinction matters. In experiments, we see strange behavior that challenges time. A particle can tunnel through a barrier that it classically shouldn't pass. It seems to appear on the other side without spending any time in the middle. What does that say about time in a quantum transition? Or consider the quantum Zeno effect. If we observe a system frequently enough, we can freeze its evolution. In other words, by watching closely, we can stop time. This isn't science fiction. It's been demonstrated in lab experiments. Measurement affects time. Observation alters duration, and that means our role as observers is deeply entangled with the flow of time itself. These are not fringe ideas. They are at the heart of some of the deepest puzzles in physics. What is time, if it cannot be observed? What is a moment, if it contains no motion? At the quantum level, the arrow of time may not exist. The equations that govern particles are symmetrical in time. They do not care whether events unfold forward or backward. But at larger scales, we see a clear direction. Entropy increases, memories form, causes precede effects. So where does this arrow begin? Some theories suggest it arises from quantum decoherence, the process by which quantum systems interact with their environment and lose their quantum behavior. As systems decohere, they become classical. Probabilities collapse into outcomes, and with that, a direction appears. Decoherence explains why we don't see cats in superpositions and why time seems to flow one way. But it also raises a disturbing thought. Is time just a symptom of losing information? And yet, quantum time isn't only strange. It may also hold answers. If time is emergent, then perhaps the flow of time is not universal, but local. Different parts of the universe may experience different clocks, not just because of gravity, but because of quantum structure. Maybe the cosmos is stitched together, not with a single clock, but with many overlapping rhythms, like a symphony with no conductor. Some physicists now speak of quantum causal structures, systems where cause and effect are not fixed in order. In these models, event A may influence event B, but event B may also influence A. This is not science fiction. It arises naturally in certain quantum experiments. In 2019, researchers demonstrated a setup where the order of two operations was undefined, both occurred, but without a fixed sequence. In such a world, the past and future are not fixed coordinates. They are fluid, entangled, contextual. So what does all this mean for time? It may mean that our everyday experience of now, of before, of later, is a kind of approximation, a simplification of a much richer, stranger foundation. Time may not tick. It may ripple. It may emerge from correlations rather than clocks, and deep within the quantum fog, it may not exist at all. But if time is not fundamental, how do we live in a world that feels so deeply temporal? How do we reconcile our internal clocks, our memories, our stories, our choices, with a universe that may not recognize those directions? Perhaps the answer lies not in rejecting time, but in embracing its mystery. To understand quantum time is to accept that the fabric of reality may not be made of things and events, but of possibilities and relationships. At the smallest scales, certainty fades, sequence blurs, and what remains is connection. Time, then, is not just what passes, it is what relates, what orders, what binds. And from that binding emerges the dance of cause and effect, of before and after, of becoming. We may never stand outside of time, but through quantum theory, we can begin to see its edges and imagine what might lie beyond. Not just seconds, not just sequences, but a universe woven with the potential for time, or its absence. Now we look inward, into ourselves, to understand how the brain perceives time, and how consciousness creates the illusion of the present moment. Chapter 16. The Mind's Clock. How the Brain Builds Time. You don't see time, you don't touch it, or hear it. And yet it's always there, an invisible thread running through your life. But where does your sense of time really come from? The world outside may unfold in moments, but the experience of time is something your brain creates. Not passively, not perfectly, but actively, interpreting, guessing, assembling a timeline from fragments of sensation. Time, for us, is not just a dimension, it is a feeling. You wake up before your alarm. You sense when someone pauses too long. You feel when minutes drag or fly past unnoticed. These aren't accidents. They are patterns, neural rhythms, chemical clocks, distributed systems working together to build your inner chronology. The brain does not store time in one place. There is no master clock, no single region that handles time like a stopwatch. Instead, time perception emerges from many systems acting in concert. One of the core contributors is the cerebellum, a structure at the back of the brain, long known for motor control. But it also helps with predicting intervals, like the gap between footsteps or the rhythm of music. The basal ganglia, deep in the brain, are involved too. They help process timescales ranging from milliseconds to seconds. And the prefrontal cortex, our center for attention, planning and awareness, tracks longer durations, like waiting, estimating, or anticipating. Together, these regions synchronize signals, accumulate inputs, and produce what we call the sense of time passing. But the brain doesn't just record time, it edits it. Experiments show that your brain adjusts your perception of duration depending on what you're paying attention to, how much happens in a moment, and even how emotionally intense the experience is. When something frightening occurs, time seems to slow down. That's not because your internal clock speeds up. It's because your brain takes in more details, laying down denser memories, making the moment feel longer in retrospect. Conversely, when life is routine, your brain compresses time. Few new memories are made. Entire days can blur. This explains why time feels faster. As we age, fewer novel experiences, less memory density, more compression. Your sense of the present, the now, is also a construction. The brain collects sensory inputs from vision, hearing, touch, and more. These arrive at different speeds. Light reaches your eyes faster than sound reaches your ears. Touch signals travel slowly from your feet. faster from your fingers, yet you don't perceive the world as out of sync. You experience it as one seamless moment. How? Because your brain waits. It holds on to faster signals for a fraction of a second, just long enough to line everything up. This is called the temporal binding window, a short period in which the brain integrates inputs into a unified perception. That delay, about a few hundred milliseconds, means you're always experiencing the world slightly behind real time. But your brain doesn't tell you that. It gives you the illusion that you're in sync with the present. In fact, it smooths over the gaps, edits out the inconsistencies, and hands you a polished version of reality. In this way, your sense of time is more like film editing than clock reading. Sensory snapshots are spliced together into what feels like a continuous reel. And just like in movies, your brain uses context, expectation, and prior experience to fill in the blanks. This is why magicians can fool you, why optical illusions can distort motion, and why traumatic events can feel slow and vivid. Your brain is reassembling time to make sense of what it believes is happening. Memory plays a powerful role here. We often think of memory as a record of the past, but it's also a tool for predicting the future. The hippocampus, a region critical for memory, activates not just when recalling events, but when imagining what's to come. In fact, the same neural pathways are used for past and future. This is called mental time travel. You simulate possibilities by replaying experiences, remixing them, and projecting outcomes. So time, for the brain, isn't just a line, it's a loop, a feedback system that lets you prepare for what hasn't happened by remembering what has. But memory is flawed. It decays, distorts, and reconstructs. You don't remember events as they were, you remember them as your brain reshaped them. Each time you recall them, every retrieval is a rewrite, and that means your past isn't fixed. It's fluid. This reshaping affects how you perceive time. An event you revisit often can feel closer than it is. A moment you avoid can fade unnaturally fast. So your internal timeline isn't linear. It's warped by emotion, repetition, and meaning. There's also the question of conscious will. When you decide to act, to move your hand, to speak, to reach, your brain begins the process before you feel you made the choice. In studies, electrical activity predicting a decision is detectable before the person reports being aware of it. This delay is milliseconds, but measurable, and it suggests that conscious time lags behind neural time. You act first. Then you feel you decided. This has sparked debates about free will, but it also reveals how the brain manages timelines. It stitches cause and effect into a coherent narrative, even if the data arrive out of order. So when we talk about the present, we are talking about a carefully edited moment, a balance of perception, prediction, and memory designed to help you survive. The now isn't a point, it's a window, a span of moments your brain treats as one. For most people, this window lasts about 2 to 3 seconds. It's within this frame that we feel musical rhythm, form impressions, and register brief events. Longer than that, and the moment breaks apart. Shorter, and we can't connect experiences. The brain's clock is not universal. It's tuned to function, to meaning, to survival. So what happens when that system breaks? In conditions like Parkinson's disease, time perception can become distorted. Moments feel faster or slower. In schizophrenia, the order of events may blur, voices seem out of sync, intentions misaligned. Drugs like LSD or psilocybin can expand or contract subjective time, creating minutes that feel like hours, or hours that pass in seconds. And trauma can fracture time completely. Moments freeze, replay, or vanish. These are not failures of reality. They are disruptions in the machinery that builds time inside your mind. Still, the brain is flexible. It can recalibrate, train, adjust. Musicians and athletes, for example, can develop fine-tuned temporal sensitivity, not just noticing time, but shaping it. Even meditation practices can slow the felt pace of time, expanding awareness into the present moment. So the mind's experience of time is not fixed. It is plastic. It bends with attention, with emotion, with purpose. And that may be the most remarkable part of all. While physics debates whether time is fundamental, your brain lives it, feels it, navigates it, all the time. Even when you're unaware, your body runs on rhythms, heartbeat, breath, circadian cycles, chemical pulses. These biological clocks interact with your mental clocks, forming a layered rhythm that shapes your sense of being. And in those rhythms, you construct meaning, not from the ticking of seconds, but from the weight of moments. Time to the brain is not just what happens, it's what matters. We remember what hurt, we cherish what shined, we anticipate what may be. The mind does not mark time equally, it elevates, flattens, and stretches, depending on relevance, and in doing so, it creates a timeline that is deeply human, not scientific, but lived. Next, we zoom back out to examine how civilizations have measured time, from the earliest sundials to atomic clocks, and how the quest to track time has shaped the modern world. Chapter 17: The Invention of Time. How humanity measured the unseen. Before people understood time, they saw it in the sky. Long before clocks, long before calendars, there was only the cycle of light and dark, the daily rhythm of the sun's rising and setting, and the slow shifting of the stars overhead. Nature provided the first clocks. The sun marked days, the moon counted months, the stars traced out the seasons. But to turn that rhythm into measurement, humans had to invent the idea of time itself. Time was not just passing, it was something to be divided, tracked, remembered. And once that shift occurred, everything changed. The earliest timekeeping tools were shadows. In ancient Egypt and Babylon, people marked the passage of the sun using simple sticks, numens planted in the earth, that cast shadows across marked lines. These sundials were not portable, and they didn't work at night, but they introduced the concept of splitting the day into segments. By dividing the arc of the sun into equal parts, people began to define hours. These hours were not fixed in length. They changed with the seasons, growing longer in summer, shorter in winter. Still, this was a revolution, the first effort to tame time. Later, water clocks emerged. In Mesopotamia, Egypt, and China, clever vessels were built that dripped water at a steady rate. As the water level rose or fell, it passed marked intervals, a fluid way to count minutes or hours. Unlike sundials, these clepsydras worked at night, indoors, and on cloudy days. They allowed for more consistent tracking, especially in religious rituals, legal arguments, and military planning. Sand clocks, or hourglasses, would arrive much later. They used the flow of granular material to measure a fixed interval, simple, elegant, repeatable. These inventions reflected a growing need for precision, a growing awareness that time was not just a backdrop, but a tool. Time became political, it became social, it became a shared rhythm by which cities lived and societies functioned. In medieval Europe, cathedrals began to ring bells to mark hours of prayer. These bells divided the day, calling people not just to worship, but to order their labor, their meals, their sleep, but without mechanical precision. These times were approximate. Then came the mechanical clock. Around the 13th century, engineers in Europe began building gear-driven clocks powered by weights. These tower clocks didn't tell minutes, they struck hours, but their gears ticked with regularity. Their escapements counted oscillations, and for the first time, people heard time, tick by tick, second by second. Life began to be measured. Time was no longer tied to nature, it could now be produced, and with production came synchronization. Cities adjusted their clocks, workers followed factory bells, ships set schedules. The Industrial Revolution made time a commodity. Train timetables required standardized time. No longer could each town use its own local noon. In the 19th century, railroad expansion in Britain forced the creation of Greenwich Mean Time. Suddenly, time wasn't just local, it was national. And then, it became global. With the rise of long-distance communication, time had to be coordinated across continents. In 1884, an international conference established 24 time zones, all anchored to Greenwich, England. This was the beginning of global standard time. From then on, the sun no longer decided the hour, the clock did. and the clock itself kept evolving. Mechanical accuracy had its limits. Pendulum clocks, developed by Christian Huygens in the 1600s, offered incredible precision for their time, but were still affected by temperature, humidity, and vibration. In the 20th century, the invention of the quartz clock changed everything. Quartz crystals, when electrified, vibrate at a precise frequency. This piezoelectric effect enabled clocks that were small, durable, and far more accurate. Wristwatches became reliable. Broadcast schedules could be trusted. Electronics could operate on tightly controlled pulses. But even quartz wasn't the final step. For ultimate precision, we turned to atoms. In 1967, scientists redefined the second as the time it takes for a cesium-33 atom to oscillate 9,192,631,070 times. This became the basis of the atomic clock. It is so stable that it loses only 1 second every 100 million years. This level of accuracy is what powers GPS satellites, coordinates financial transactions, and regulates telecommunications. Your phone's clock, your laptop, your digital world, all synchronized by atomic pulses. But the pursuit of perfect timekeeping hasn't stopped. Modern laboratories now develop optical lattice clocks, which measure the vibrations of atoms using lasers at even higher frequencies. These clocks could be accurate to 1 second in the lifetime of the universe. Why such precision? Because with time that fine-grained, you can detect gravitational changes, map Earth's shape, and test the very foundations of physical laws. And yet, even with all this control, time remains elusive. As our clocks get better, we learn that time is not the same everywhere. Einstein showed that time is relative. It runs slower in stronger gravity, and at higher speeds. This means your head ages slightly faster than your feet. An airplane passenger lives a few nanoseconds longer than someone on the ground. These differences are real, measurable, and crucial for technology like GPS. So what then is a second? It is not a universal tick. It is not written into the cosmos. It is a human choice, a definition based on a stable, repeatable event. We build our lives on these events. We divide time into units: seconds, minutes, hours, days, years. We chart our histories, our futures, on a grid we made. But nature knows no such calendar. There is no cosmic clock. There is only change. And still, we persist in measuring. We track lunar cycles, solar rotations, planetary alignments. We mark birthdays, anniversaries, deadlines, and lifetimes. Time has become a scaffold for meaning. It is how we anchor memory, how we set goals, how we narrate identity. And in every measurement, we bring order to the unknown. Not because the universe demands it, but because we do. Timekeeping is more than science. It is culture. It is ritual. It is power. Kings declared calendars. Religions defined holy days. Empires imposed time as part of conquest. Even today, the time zones we live in are shaped by politics, colonial legacies, and borders. Time is not neutral. It reflects who controls the clock. And yet, beneath the layers of precision and tradition, there remains a simple truth. Our need to measure time is born from our awareness of its passing. We count time because we feel it slipping. We build clocks, not to trap it, but to witness it. Every tick reminds us we are here now, and this moment will never come again. Now, we return to a deeper mystery, the direction of time. Why does it always seem to flow forward? And what does the science of entropy tell us about time's arrow? Chapter 18. Entropy and the Arrow. Why time moves forward. Time feels like motion. It feels like direction. You wake up, eat breakfast, grow older. You move through life one way, forward. Memories accumulate behind you. The future remains out of reach. You cannot undo a word once spoken. You cannot unbreak a glass once shattered. This directionality of time, this sense that the past is fixed, and the future uncertain, seems obvious. But when we examine the laws of physics, a strange fact emerges. Most of them don't care about direction. The equations that describe motion, gravity, electromagnetism, and even the forces that bind particles, all work the same, whether time moves forward or backward. You could reverse time in Newton's laws, and everything would still hold. A falling apple could rise back to the tree, the wave could crash and uncrash. A planet's orbit could reverse itself without breaking the rules. So why, in reality, does time seem to go only one way? What gives the universe its temporal asymmetry? The answer, for many scientists, comes down to a single word: entropy. Entropy is not disorder. Exactly. It's not chaos. It's a measure of how many possible microscopic arrangements can produce the same macroscopic outcome. In other words, entropy counts the number of ways you can shuffle the unseen details without changing what you observe overall. And over time, in a closed system, entropy tends to increase. This is the second law of thermodynamics, and it may be the source of time's arrow. Imagine a deck of cards, perfectly ordered, aces on top, suits aligned. That arrangement is low entropy, only one of many possible ways the deck could be stacked. Now shuffle the cards. There are billions of new possible orders. The deck becomes high entropy, more randomized. It's not impossible to return to the original order, but it's incredibly unlikely. The second law doesn't say that disorder must happen. It says that more probable states will tend to emerge over time. That's why ice melts, why perfume spreads in a room, why heat flows from hot to cold. Entropy is not a force. It is a tendency, a statistical truth about how systems evolve. And that tendency gives time its arrow. When entropy increases, we feel time moving forward. When we see a dropped glass shatter, we understand what came before, a whole glass. But if we saw shattered pieces fly back together into a perfect glass, we'd know something was wrong. Not because it's physically impossible, but because it's statistically absurd. In this view, the past is low entropy, the future is high entropy, and time flows in the direction of increasing entropy. But this raises a deeper question. If time's arrow depends on entropy increasing, then why did the universe start in a low entropy state? Why was the beginning so improbably ordered? After all, the early universe was hot, dense, and uniform. A smooth soup of particles. That sounds high entropy. But gravity changes the rules. In a system governed by gravity, clumping leads to higher entropy. Stars forming, galaxies assembling, black holes emerging. A smooth distribution of matter is gravitationally low entropy. So the early universe was astonishingly ordered. That order is what gives rise to the flow of time we now experience. This is still a mystery. We don't know why the universe began in such an improbable state. Some theories suggest this initial condition was random, a fluctuation in a timeless quantum field. Others propose that time itself emerged at the Big Bang, and that asking what came before has no meaning. Still others suggest that our universe is just one region in a much larger multiverse, and we happen to live in a bubble where low entropy conditions allow time to flow. Whatever the explanation, the second law holds. Entropy increases, ice melts, stars burn out, memories accumulate in one direction. Even in black holes, entropy plays a role. Stephen Hawking showed that black holes have entropy proportional to the area of their event horizons. This was one of the great insights connecting thermodynamics, gravity, and quantum theory. Black holes evaporate slowly over time, radiating energy in a process that increases the total entropy of the universe. And eventually, if left alone, they too disappear. This leads to one of the most haunting ideas in physics, the heat death of the universe. If entropy always increases, then eventually the cosmos may reach a state where all energy is evenly distributed. No stars, no movement, no gradients, no information processing. A cold, dark, flat universe at maximum entropy. Time in such a state would lose all meaning. Nothing would change, no events would occur, and the arrow of time would dissolve. But we are not there yet. We live in a universe rich with gradients. Hot and cold, bright and dark, simple and complex. Life itself depends on entropy. We extract usable energy from ordered systems, food, sunlight, fuel, and expel waste heat into the environment. We are tiny engines of entropy production. Every breath, every thought, every heartbeat pushes the universe a little further along its path. Entropy does not mean death. It means change. And in that change, we find meaning. Entropy also explains why we remember the past, but not the future. When we form a memory, we record information. That process increases entropy. It leaves a physical trace in neurons, in synapses, in material configurations. To remember the future, we'd need a system that anticipates specific outcomes before they occur. Such systems are not forbidden, but they are exceedingly rare. The second law makes the past a place we can record, but the future a realm of uncertainty. That's why we look back and only guess forward. Entropy also connects to information theory. In physics, entropy and information are deeply intertwined. A highly ordered system contains less information because there are fewer ways it could be arranged. A messy, complex system contains more potential information. So when we say entropy increases, we're also saying the number of possible microstates grows over time. The future in this sense is a realm of expanding options. It is not predetermined. It is rich with probability. And perhaps this is what time really is. Not a ticking clock, but a widening horizon. A movement from fewer possibilities to more. A blossoming of states. A diffusion of energy. A story that unfolds from simplicity to complexity. From birth to decay. And within that flow, we exist. Not in defiance of entropy, but because of it. Our lives may be brief. Our structures temporary. Our plans prone to dissolution. But the very laws that guarantee our impermanence also allow for consciousness, creativity, and memory. We are not outside of entropy. We are its children, born of a low-entropy past, moving through a universe that becomes more possible with every passing second. So the arrow of time is not just physics, it is poetry. It is the story of the universe, learning how to remember itself, through matter, through light, through life, through life. Next, we explore how time shapes us as individuals, how we think about our past, plan for our future, and find meaning in the fleeting present. Chapter 19. Living Time, Memory, Identity, and the Flow of Self. Time does not simply pass. It lives inside us. It is in the way we remember our childhood, in the way we worry about tomorrow, in the way we construct who we are, based on what we've been through, and what we hope to become. Time is not just out there in the stars and clocks and calendars. It is in the mind, a stream of experience that flows through memory, emotion, and awareness. You do not feel time as a measurement. You feel it as story. You do not wake up thinking 7 hours have elapsed. You wake up remembering a dream you had, a deadline today, a conversation from yesterday. Your identity is made from the fragments of your past, stitched together into something that feels continuous, a self. But this continuity is a brilliant illusion. There is no single spot in the brain where you reside, no hard drive where your life is stored, no timeline etched into your biology. What we call self is a process, a constantly updating narrative that uses memory to simulate permanence. Your brain keeps that story alive by constantly predicting. Right now, you are not just hearing these words, you are anticipating the next one. Your attention flows forward, just ahead of the moment, expecting what's to come. You imagine outcomes, so you can act. You compare what happens to what you predicted. You update, you adapt. This constant cycle, prediction, outcome, revision, is how you live through time. But that process is not perfect. Sometimes we replay the past too often. Sometimes we fear a future that hasn't arrived. This is the psychological burden of time. We carry it like a weight. Not just the hours we must endure, but the versions of ourselves we think we should have become. Regret looks backward. Anxiety looks forward. Peace lives in the rare moment when past and future fall silent. Still, we rely on memory to construct meaning. Memories are not just records. They are how we know what matters. You remember your first heartbreak, your child's first steps, the day someone said goodbye. These events are stored, not because of how long they lasted, but because of how deeply they shaped you. Emotion marks memory. The stronger the feeling, the stronger the trace. And over time, we rewrite those memories. Not to falsify them, but to survive them. That is the paradox of psychological time. It bends. Some days fly by, others stretch endlessly. A week in grief can feel longer than a year in routine. This is because time is not a substance you move through. It is an experience shaped by context, engagement, and attention. When you're fully immersed, you lose track of time. When you're bored or in pain, you feel every second. The same clock ticks on, but the mind experiences it differently. This variability is deeply human. It allows us to find meaning, not just in what happens, but in how we remember it. Some cultures even perceive time differently. In English, we speak of the future as ahead of us, and the past behind. But in Aymara, an indigenous language of South America, the past is described as being in front, because it is visible, known. The future, unknown and unseen, is behind. This reversal reminds us that time is not only measured, it is interpreted. Your sense of time also changes across your lifespan. For a child, a year feels like a vast ocean. New experiences, rapid growth, endless discovery. For an older adult, a year may pass in what feels like a breath. This is not just perception, it is neural economy. As we age, fewer novel events occur. The brain compresses familiar patterns. Time feels faster, because fewer new memories are created. We call this the reminiscence bump, the tendency to remember adolescence and early adulthood more vividly than any other time. Not because they were better, but because they were new. But time is not just memory, it is hope. We are creatures wired to imagine what comes next. We plan, set goals, dream of what could be. This ability to project ourselves into the future is what separates us from most other animals. It allows for civilization, for progress, for art and science, and stories like this one. But it also opens the door to fear and disappointment. We imagine not just success, but failure, not just joy, but loss. Still, we return again and again to the same truth. We live in time, but we also shape it. Your schedule, your past, your memories, your dreams, all emerge from a brain trying to make sense of a world that never stops changing. You are not just the sum of your yesterdays. You are the author of how you interpret them, and you are the architect of what comes next. Even in stillness, the mind moves. Even in silence, time flows. You close your eyes and hours pass. You wake up changed. The body ages, the brain rewires. The self evolves. And in all that shifting, you still feel like you. This is the quiet miracle of psychological time. The fact that identity can persist even as everything else transforms. But there is one moment where time disappears, or at least where it ceases to matter. In meditation, in deep focus, in love, in awe, the self dissolves. We call this flow. Psychologists describe flow as a mental state where time becomes irrelevant, action becomes effortless, and awareness merges with the task. In flow, you don't track time, you become time. Not in minutes or hours, but in pure presence. And perhaps that state is a clue. Maybe the true secret of time is not how to measure it, but how to live inside it fully. You cannot stop time, but you can stop running from it. You can sit quietly, watch a leaf fall, feel your heart beat, listen to someone breathe beside you. In those moments, time softens. It becomes something not to fight, but to hold, not to control, but to witness. And in that witnessing, you find meaning, not in clocks, not in calendars, not in milestones, but in attention, in connection, in awareness. Time lived, not counted. Time remembered, not wasted. Time loved, even as it passes. Next, we look at how the future of time itself may evolve, as artificial intelligence, space travel, and time manipulation begin to challenge our deepest assumptions about how reality unfolds. Chapter 20. The Future of Time. Machines, Space, and the End of Now. Humanity has always tried to control time. We measured it with shadows, we tracked it with gears, and now we digitize it down to the smallest imaginable unit. But as technology advances, something unexpected is happening. Time is beginning to feel less like a natural force, and more like a programmable system. We are not just observing time anymore, we are rewriting our relationship with it. Consider artificial intelligence. AI does not perceive time the way we do. It does not grow tired. It does not sleep or age. It processes information in parallel, not sequentially. For machines, tasks that take humans hours can be completed in seconds. Entire libraries of knowledge can be absorbed in a fraction of a moment. This shift creates a new kind of time gap, not between generations but between humans and their machines. We are entering an era where our tools operate in a temporality that feels alien to our biology. With AI managing workflows, predicting decisions, and shaping our environments, time is no longer just something we experience. It is something we are increasingly outsourcing. You don't remember birthdays. Your phone does. You don't decide when to rest. Your smartwatch tells you. Our time is being packaged, tracked, optimized, and in some cases sold. Data becomes the currency of time, and attention becomes its price. And yet, while AI compresses time, space travel stretches it. Einstein's theory of relativity tells us that time runs differently, depending on speed and gravity. As we venture further from Earth, these effects become more than theory. Astronauts aboard the International Space Station age ever so slightly less than people on the ground. Their clocks tick more slowly, even though they don't feel it. This phenomenon, time dilation, is not just an abstract idea. It is measurable. It is real. And it becomes even more extreme at higher velocities, or near massive gravitational fields. Imagine a future where humans travel to distant stars at a significant fraction of the speed of light. To those on board, a year might pass. To those on Earth, decades could go by. This is not science fiction. It is a consequence of the way time behaves when you push the boundaries of space and speed. If we ever become a spacefaring civilization, we will no longer share a single now. The idea of a universal present, a shared global moment, already feels strained in a world of instant messaging, satellite communication, and virtual collaboration. But in a future of deep space travel, it may vanish entirely. Families may split across timelines. Colonies on distant planets may evolve calendars based on their own rotation and revolution, and Earth may become just one clock among many. We may even reach a point where time is engineered. In highly advanced labs, scientists are already experimenting with quantum time crystals, structures that may exhibit motion without energy input, potentially bending our understanding of periodicity and stability. While still theoretical, these ideas suggest that time itself might not be a fixed backdrop, but something that can emerge, be reshaped, or even created. As our tools evolve, so do our metaphors. The ticking clock is being replaced by algorithms, simulations, and event streams. We used to describe time as a flowing river. Now we describe it as a data pipeline, as a networked system, as a sequence of computational states. Time becomes not just something you travel through, but something that gets processed, versioned, or even paused. In virtual reality, you can slow time, speed it up, or reset it entirely. Entire experiences can be stored, replayed, or modified. If memory was once the only way to revisit the past, digital records now offer an archive more detailed than our brains could ever provide. Emails, texts, videos, biometrics, they all leave traces, and artificial intelligence may soon be able to simulate your past decisions, reconstructing versions of you that behave just like your present self. This raises questions not only about time, but about identity. If a copy of your mind can be run again in the future, has time really passed for that version of you? This opens the door to digital immortality. Some futurists envision a world where your consciousness is uploaded, stored as code, replicated, and potentially reactivated after biological death. If that happens, your timeline might never end. But would that be you, or just a reflection frozen in the logic of machine time? We are not built to live forever. Our sense of meaning is intimately tied to the finiteness of life. If time no longer ends, does purpose vanish too? On the other side of the spectrum, climate change is teaching us that the future is no longer far away. What once felt distant, rising seas, mass extinction, global shifts, is now entering the present. The time horizon is collapsing. We can no longer afford to live only in the now. The future is knocking on today's door, and it demands that we take responsibility, not just for our own lifetimes, but for generations we may never meet. In this way, technology gives us power, but also pressure. The more we control time, the more we are asked to think long-term. Should we build data centers that last centuries? Should we preserve languages that might otherwise vanish? Should we encode our knowledge so that future intelligences, biological or artificial, can understand it? These are not abstract questions. They are being asked right now by engineers, philosophers, and archivists who believe that time is not only measured, it must be stewarded. And so, we stand at a strange moment. We have clocks that lose less than a second in the age of the universe. We have machines that move faster than our minds. We have data that may outlive our species. And yet, we still mark time with birthdays, with sunsets, with silence. For all our advances, we remain creatures of rhythm. We wake, we work, we run, and somewhere inside us, we still carry the pulse of a universe that began with a single unfolding moment. Perhaps the future of time is not about conquering it. Perhaps it is about aligning ourselves more deeply with its truth, not the clock's truth, not the algorithm's truth, but the truth of impermanence, of motion, of becoming. To live well in time may not mean slowing it down or escaping its grasp. It may simply mean being present as it carries us forward. You are not falling behind. You are not running out. You are moving through time, exactly as everything does, with wonder, with change, with the quiet knowledge that nothing stays, but everything matters. Next, we descend into one of the strangest frontiers of time, how quantum mechanics challenges the very idea that events happen in a fixed order, and what it means to live in a world where time may not be linear at all. Chapter 21: Quantum Time. When cause and effect break down. At the scale of the everyday, time feels like a river, steady, predictable, flowing from past to future. You wake up, you eat breakfast, you carry out your plans in the order you expect. But in the world of quantum mechanics, the idea of a fixed sequence of events starts to unravel. Cause and effect, which once seemed like the foundation of reality, begins to blur, and time itself no longer behaves like a straight line. In classical physics, time is a clean parameter. It moves in one direction, and everything else plays out within it. You drop a ball, it falls. You light a match, it burns. The sequence is clear, irreversible, and ordered. But in the quantum world, particles do not follow simple trajectories. They exist in superposition states that are both here and there, spinning this way and that, until observed. And when you measure them, you collapse that ambiguity into a single outcome. That moment of measurement defines the outcome, but it also defines when the outcome occurred. This is where things begin to shift. In some experiments, changing the setup after a particle has passed through can still influence the result you get. It's as if the decision you make now reaches back in time to shape what happened before. This is known as the delayed choice experiment, first proposed by physicist John Archibald Wheeler. The setup is simple, but the implications are anything but. A photon, a particle of light, is sent through a device that can act either like a path splitter or a path merger. If you look for which path it takes, the photon acts like a particle. If you don't look, it acts like a wave, interfering with itself. But in the delayed choice version, you decide after the photon has entered the setup whether to observe which path it took. Astonishingly, the outcome still changes. It's as if the photon waits until you make your decision, even though that decision comes too late in any classical sense of time. This challenges the notion that events have a strict temporal order, and it raises a strange possibility that the flow of time we experience may not exist in the quantum realm at all. Instead of a fixed sequence of events, quantum systems seem to operate in a kind of timeless space of possibilities, where outcomes emerge only when conditions are right to observe them. This idea becomes even stranger in a newer branch of research called indefinite causal order. In classical systems, if event A causes event B, then A comes first, B comes second. But in some quantum experiments, this clear order disappears. Physicists have built setups where two events influence each other without a defined sequence. The order is not just unknown, it's undefined. Imagine sending an email and receiving a reply before you pressed send, or being both the cause and the effect in a single transaction with no clear beginning. That's what indefinite causal order implies, and as bizarre as it sounds, it has been demonstrated experimentally. One experiment used a device called the quantum switch. It allows two operations to happen in an order that is in superposition, A then B, and B then A, both at once. When measured, the system collapses into one sequence or the other. But until then, both orders coexist. This isn't just theoretical trickery. It has real implications for how quantum information is processed, and it may become a cornerstone of future quantum computers. But what does this mean for our experience of time? At the quantum level, time may not be fundamental. It may be emergent, a property that arises only when enough particles interact in the right way. Some physicists even propose that time, like temperature, is a macroscopic phenomenon. Just as temperature emerges from the motion of atoms, time might emerge from the entanglement and correlation of quantum events. In this view, time is not a backdrop. It is a result. This connects to another mystery: the problem of time in quantum gravity. In general relativity, time is part of the fabric of spacetime. It bends, it slows, it interacts with matter. In quantum mechanics, time is treated as external, a parameter that isn't itself subject to uncertainty. When scientists try to combine these two theories into one unified model, the definition of time becomes fuzzy. In some formulations of quantum gravity, like the Wheeler-DeWitt equation, there is no time variable at all. The universe is described by a static wave function, a kind of cosmic probability map, where everything simply exists. If that's true, then the universe as a whole may be timeless, and the flow of time that we experience could be just a trick of perception, a slicing of this wave function into a sequence of moments our brains can understand. This doesn't mean time is fake. It means that time may be deeply connected to observation. To be aware is to create order. To observe is to define when. Even time travel, once thought impossible, is being re-examined in light of quantum theory. Some models allow for closed time-like curves loops in spacetime, where particles or information could in theory return to their past. In quantum mechanics, this might not violate causality. Instead, it could allow for consistent histories, scenarios where the future influences the past, without creating paradoxes. One version of this, proposed by physicist David Deutsch, suggests that information sent back in time would always resolve into a consistent outcome. In other words, you could not kill your own grandfather, because the probability of doing so would cancel itself out. These are not practical blueprints for building time machines. They are mathematical suggestions that the rigid barrier between past and future might be softer than we think. And while none of these ideas have yet produced a working experiment that lets us step outside time, they do tell us something profound. Time, at the smallest scales, is not a line. It is not a rule, it is a possibility. The idea that time is a human-scale illusion is not new. Philosophers have long argued that past, present, and future might all exist simultaneously, and that our consciousness simply moves through them, like a light scanning a film reel. Quantum physics does not prove this, but it invites us to ask whether what we feel as now is something objective or something constructed, and it reminds us that the universe at its core may not follow the same logic that our lives are built upon. Still, even in this quantum world of reversals, loops, and undefined orders, we continue to feel time. We wake each day with memories and expectations. We walk into the future with no idea what comes next. And in the vast field of quantum possibility, this feeling, this sense of presence, might be the only thing truly. Next, we explore how time behaves in the most extreme environments of all. Inside the crushing gravity of black holes, where time doesn't just stretch or bend, it may come to a complete stop. Chapter 22, Time at the Edge. Inside black holes and the end of clocks, imagine a place where the rules of physics begin to unravel, where gravity is so strong that not even light can escape, where space itself twists and collapses inward, and where time, as we know it, begins to break. This is a black hole, a region in space where time behaves not just differently, but almost unimaginably. It is not simply a void, it is a region where the fabric of reality is bent so tightly that time becomes warped to its most extreme degree. To understand why, we need to revisit Einstein's general theory of relativity. In this theory, mass and energy curve space-time. The more massive an object, the more it bends the geometry around it, and the more that curvature increases, the more time slows. You can think of time as a flexible dimension, not fixed like a metronome, but influenced by the presence of gravity. Near Earth, this effect is tiny but real. A clock on a mountaintop ticks ever so slightly faster than one at sea level, but near a black hole, the difference becomes enormous. As you fall toward a black hole, an outside observer would see your movement slow. Your clock ticks more gradually. Your heartbeat spaces out. Your fall appears to take forever. You seem frozen just outside the event horizon, the boundary of no return. From your perspective, nothing feels strange. You fall freely. Your watch keeps ticking normally. But to someone watching from a safe distance, your time slows, then nearly stops. This isn't a trick of the eye. It's real physics. And at the event horizon itself, time as measured from the outside stops entirely. This leads to a strange idea that the surface of a black hole is not just a boundary in space, but a boundary in time. It separates events that can be observed from those that cannot. It divides the universe into what remains knowable and what disappears beyond the veil. But what happens to time inside the black hole? Here our equations become unstable. General relativity predicts that all matter and energy collapse into a single point, a singularity, infinitely dense, infinitely small, where the curvature of space-time becomes infinite. At the singularity, time and space no longer behave in any recognizable way. Many physicists believe that at this point, our current understanding of physics fails. We need a new theory, one that merges quantum mechanics with general relativity. Until then, we cannot say for certain what happens inside the core of a black hole. But some things are clear. The direction of time, the arrow we follow from past to future, is twisted by gravity. Inside a black hole, the flow of time and the pull of gravity point in the same direction. They both lead inward. That means moving forward in time also means moving toward the center. You cannot escape, because escaping would require moving backward in time. This is a radical shift. Outside a black hole, you can choose to go forward, backward, left, right, up, or down. Time moves forward for everyone, but space offers options. Inside the event horizon, the geometry reverses. Time still moves forward, but now, forward is toward the singularity. You are pulled inward, not just by gravity, but by time itself. There is no trajectory that avoids the center. Just as you cannot stop time on Earth, you cannot stop falling inside a black hole. And yet, black holes do not just devour, they also radiate. Stephen Hawking, combining quantum field theory with curved spacetime, predicted that black holes emit energy. This process, now known as Hawking radiation, means that black holes are not eternal. They slowly lose mass, shrinking over billions of years, until they eventually evaporate. This revelation links three fundamental concepts: gravity, quantum mechanics, and thermodynamics. It also leads to a mystery that remains unsolved: the black hole information paradox. According to quantum theory, information cannot be destroyed. If something falls into a black hole, that information, its physical state, its quantum configuration must be preserved. But general relativity seems to suggest that once something crosses the event horizon, it is lost forever. If the black hole eventually evaporates, where does that information go? Does it escape with the radiation? Is it smeared on the surface of the black hole? Is it preserved in some holographic form? No one knows for sure, but the implications are deep. Time is not just about sequence, it is about information. It is about knowing what happened and predicting what might. If black holes erase information, they might also challenge our very definition of time. Some physicists now believe that information is not lost, but encoded on the boundary of the black hole in a kind of hologram. This leads to the holographic principle, the idea that all the information in a volume of space can be represented on its boundary. In this view, the three-dimensional world we know might be an illusion projected from two dimensions, and time, in such a framework, may not be a flowing river but a coded pattern on a distant surface. This changes the way we think about reality itself. It suggests that what we call now might be a cross-section of a deeper structure, something shaped not by clocks and calendars, but by geometry, gravity, and quantum logic. Black holes are not just celestial oddities, they are windows into the most extreme aspects of time. They show us what happens when time slows, stops, and perhaps even folds in on itself. And yet, for all their strangeness, black holes still belong to the same universe we inhabit. They are born from stars, they evolve, they decay. They exist in time, but they also challenge it. They are reminders that the laws we rely on are only as strong as the questions we are willing to ask. Time may seem solid, predictable, even comforting, but the deeper we look, the more it bends. At the edge of a black hole, time does not vanish. It transforms, and in that transformation we glimpse the limits of our understanding. We realize that what we call reality may be more fragile than we ever imagined. Next, we step back from the extremes of gravity and enter the world of biology, where time is felt in every heartbeat, every breath, and every cycle of life that makes us who we are. Chapter 23, The Body's Clock, Time in Biology and the Rhythm of Life. You do not need a watch to know that time is passing. Your body tells you. It signals hunger in the morning, tiredness at night, and a gentle pulse in your chest that beats rhythm into every second. Long before civilization invented clocks, life evolved its own systems for measuring time. These systems are not made of metal or powered by electricity. They are organic, chemical, and deeply embedded within every living cell. This is biological time, an internal sense of rhythm that guides everything from sleep to metabolism, growth to decay. And while it may seem invisible, it is among the most ancient and essential features of life on Earth. The most well-known example is the circadian rhythm, a roughly 24-hour cycle that governs wakefulness, alertness, temperature, hormone production, and many other biological processes. These rhythms are not arbitrary. They evolved in sync with the rotation of the planet. As Earth turns, light and darkness alternate. Organisms adapted to anticipate these cycles, aligning their behavior with day and night. Even single-celled organisms have genes that respond to light. Plants open and close their leaves according to the sun. Humans experience fatigue when that rhythm is disrupted during jet lag, shift work, or insomnia. Our internal clock, known as the suprachiasmatic nucleus, is located in the brain's hypothalamus. It uses light cues from the eyes to stay calibrated to the external world, but light is not the only signal. Meal timing, physical activity, and social interaction can also influence biological time. Even if you live in a dark cave without access to natural light, your body will still maintain a rhythm close to 24 hours, though it may slowly drift. This ability to track time internally, without external reference, is known as an endogenous rhythm. It's built in, and it allows the body to coordinate complex tasks, even while asleep. For example, your body begins releasing melatonin before bedtime, preparing you to rest. And just before you wake, it increases your body temperature, blood pressure, and cortisol levels, so you feel more alert. These rhythms also apply to other cycles: weekly, monthly, seasonal. Some hormones rise and fall on multi-day schedules. Menstrual cycles, which are roughly monthly, affect energy levels, cognition, and immune response. And throughout the year, humans experience subtle shifts in sleep patterns, mood, and even appetite. These are echoes of an evolutionary past, when survival depended on knowing when to store energy, when to mate, when to migrate, and when to rest. But biological time is not just about cycles, it also tracks aging. From the moment we are born, our bodies begin a process of growth, repair, and gradual decline. Each cell carries a clock in the form of telomeres, protective caps on chromosomes that shorten each time a cell divides. When they become too short, the cell can no longer replicate, leading to aging at the cellular level. This does not mean we are born with an expiration date, but it does suggest that time is written into our biology in a way that is both profound and unavoidable. Other markers of biological time include the epigenetic clock, a way to estimate biological age by analyzing patterns of chemical changes in DNA. This kind of age does not always match your chronological age. Two people born on the same day may age at different rates, depending on stress, diet, exercise, and environment. This means that time, at least as your body understands it, is not always linear. It is responsive. It can be accelerated or slowed by how you live. Sleep is one of the most powerful tools for regulating biological time. During sleep, your brain cleans itself, your body repairs tissues, and memories are consolidated. Lack of sleep doesn't just make you tired, it disrupts hormone balance, weakens immunity, and increases the risk of chronic diseases. Your internal clock relies on regular sleep cycles to keep everything aligned. Disrupt those cycles too often, and the body begins to lose track of when to rest, when to heal, and when to act. This is why shift workers and frequent flyers often experience brain fog, mood swings, and metabolic issues. Their biological clock is desynchronized from the world around them. The result is not just fatigue, but a deeper sense of temporal disorientation. Time feels off, because the body's rhythms no longer match external cues. Yet, we are not prisoners of these clocks. There is evidence that meditation, exercise, and certain dietary patterns can help resynchronize the circadian rhythm. Some researchers are even exploring whether it's possible to reverse biological age by resetting cellular functions. This includes caloric restriction, intermittent fasting, gene editing, and senolytics, drugs that target aging cells. These interventions are still being studied, but they offer a tantalizing possibility that time, at least in the body, might be more flexible than we once believed. But flexibility is not the same as control. For all our advances, the passage of biological time remains inexorable. Bones become brittle, skin loses elasticity, memory becomes more selective, reflexes slow, hair grays, and yet none of these changes define your value, your purpose, or your identity. Time may change the body, but it does not erase what the body has felt, endured, and become. This perspective is important. We often treat aging as a failure of time, rather than a natural continuation of it. But in biology, aging is not decay. It is adaptation. It is the accumulation of knowledge at the cellular level. It is the living record of everything you survived. Even the wrinkles around your eyes are written in laughter, in tears, in years lived fully. And this is perhaps what makes biological time so meaningful. It is not abstract. It is not distant. It is lived. Every moment is felt through breath, heartbeat, touch, and memory. Your body remembers even when your mind forgets. It holds on to rhythms even when you stop noticing them. It is the most personal form of time. It is time made flesh. Next, we'll explore how memory, fragile yet essential, anchors our perception of time and how the brain stitches past and future into a story we call the present. Chapter 24: Memory, Consciousness, and the Illusion of Time. You close your eyes, and suddenly, you're back in a childhood room. The wallpaper, the smell of dust and sun, the sound of laughter coming from down the hall, they all return, not just as facts, but as experience. This is memory, the way your mind reaches across time and brings the past into the present. But memory is not a recording. It's not a perfect file waiting to be played back. It is dynamic, fluid, reconstructed every time you recall it. And in that reconstruction, you don't just remember time, you create it. Time in the brain is not measured in ticks or tocks. It's stitched together through patterns of perception, emotion, and association. Your brain does not feel time passing. It estimates duration based on how much information you processed during a moment. This is why a new complex experience can feel long, while routine moments slip by unnoticed. It's also why time feels slower during fear or danger. Your senses take in more. Your mind records everything. More data equals the illusion of more time. This reveals something profound. The subjective sense of time is built from attention. What you focus on, what you remember, what you feel, these are the raw materials from which the mind constructs a timeline. Without memory, there is no continuity. Without continuity, there is no self. Consider this. You are not just the person sitting here now. You are also every moment you remember. The story your mind tells to bridge one moment to the next. And that story is not written in stone. It shifts, it blurs, it rewrites itself. When you recall a memory, you do not retrieve it unchanged. You rebuild it, piece by piece, informed by who you are now. Then, your brain saves that new version, which means, each time you remember, you slightly alter what you remember. It is not a flaw, it is how human memory works. It allows you to adapt, it allows you to learn, but it also means that the past is not fixed. Your history is constantly being rewritten through the lens of the present. The brain's memory system relies on several structures: the hippocampus, which encodes new memories, the amygdala, which adds emotional weight, and the cortex, which integrates long-term storage. Each of these components plays a role in shaping your experience of time. Damage to the hippocampus can prevent new memories from forming, trapping a person in an eternal present. This condition, known as anterograde amnesia, has been the subject of books and films, but its reality is far stranger than fiction. Imagine meeting someone, talking with them, then forgetting that encounter a few minutes later, forever. In this state, you do not age emotionally, you do not grow in the usual sense, because you do not accumulate time. And then, there is retrograde amnesia, the loss of memories before a specific moment. People with this condition lose their personal history. They may remember how to speak, how to walk, how to eat, but not who they are. This separation between procedural memory and autobiographical memory reveals something essential. Memory is not one thing, it is many systems working together. And those systems are what make a sense of time possible. Even more mysterious is how memory interacts with imagination. When you think about the future, your brain activates many of the same regions as when you remember the past. This suggests that time travel in the mind works in both directions. You remember to imagine. You imagine by rearranging memory. This is called episodic future thinking, the ability to simulate potential scenarios based on past experience. It is what allows you to plan, to hope, to regret. It is what makes time feel like a path, rather than a prison. But what happens when that simulation goes wrong? In conditions like PTSD, memories refuse to stay in the past. Traumatic moments return with the force of present reality. They hijack the brain's timeline, forcing you to relive what you should only remember. Time collapses, and the present becomes haunted by the past. Treatments like EMDR and exposure therapy try to help the brain reclassify those events to tag them as then, not now. In doing so, they restore the barrier between memory and experience. They restore the flow of time. Memory is not just mental. It is deeply embodied. A song, a smell, a texture. These can trigger vivid recollections with no warning. This is because the brain stores memory in networks that include sensory pathways. Your body knows before your mind does. This is why nostalgia can be overwhelming. It is not just a thought, it is a wave of time moving through your nervous system. But memory is also selective. You cannot remember everything. You remember what mattered, what shocked you, what repeated, what made you feel. And even those memories fade, shift, or disappear. This is not failure, it is curation. Your mind filters the past to make sense of the present. It edits to help you survive. Yet the illusion of continuity remains strong. You feel like a single person, moving forward through time, gathering experiences, becoming wiser, growing older. But in reality, you are a new configuration of neurons, chemicals, and stories. With each passing moment, you are not who you were 10 years ago, not even 10 minutes ago. And yet, you are connected by memory. This is what creates identity. Not a permanent self, but a thread of remembered moments woven into a narrative. And this narrative is always unfolding. You recall the past, imagine the future, and in doing so, define the present. Time is not outside you. It is something you build from within. Each breath, each thought, each moment of reflection. It all becomes part of the story that only you can tell. Next, in the final chapter, we explore one of the most radical ideas of all, that time may not exist at all, and that what we call reality may be an illusion crafted by the limits of how we see. Chapter 25. Beyond Time. Is it all just an illusion? From the ticking of ancient sundials to the equations of Einstein, we've built our understanding of the universe on the assumption that time is real. It seems obvious. We grow older, we remember yesterday, we plan for tomorrow. But what if all of that, the flow, the change, the very feeling of movement, is just a trick of the mind? What if time, as we experience it, doesn't actually exist? This is not a science fiction thought experiment. It is a serious question being asked by some of the world's most respected physicists and philosophers. At the deepest levels of modern physics, there is growing evidence that time might not be fundamental. It might be emergent, like temperature, arising only when enough complexity comes together. And beneath that surface, there may be no ticking clock, no direction, no before and after, only a timeless state of being. One of the earliest clues comes from the block universe theory, which arises naturally from Einstein's relativity. According to this idea, all of time, past, present, and future, already exists. The universe is like a four-dimensional block. What we experience as now is just a slice through that block, chosen by our consciousness. Events are not happening, they simply are. Your birth, your death, this very moment, they all exist simultaneously, frozen in space-time. This view challenges our most intimate assumptions. We feel that time flows, that we are moving forward. But if the block universe is correct, then the flow of time is an illusion, a product of the way we experience the world. This doesn't mean life is meaningless. It means that time is not what it appears to be. It is not a river, it is a landscape, and we are travelers within its folds. Another theory, even more radical, comes from the world of quantum gravity, where researchers attempt to unite the laws of the very large with the laws of the very small. In some models, when you write down the equations for the whole universe, time disappears completely. The Wheeler-Deinde equation, which describes the quantum state of the cosmos, contains no time variable. It treats the universe as a single, unchanging wave function. There is no ticking clock, no timeline, no sequence. Everything just exists, all at once. If that's true, then time is not part of the ultimate structure of reality. It is something we impose to make sense of change. Like a projector casting motion onto a still reel of film, our minds animate the universe by stitching together experiences into a coherent narrative. That stitching, that feeling of time passing, may not reflect what reality is, only how it feels to be alive inside it. This may explain why different observers experience time differently, why gravity slows it, why speed stretches it. Time is not a universal constant. It bends, it shifts, it breaks. But if it were fundamental, it wouldn't be so malleable. Instead, its flexibility suggests that time is a byproduct, an emergent property of something deeper and more abstract. That something might be entanglement, the mysterious quantum connection between particles. Some researchers believe that space and time themselves emerge from networks of entangled quantum states. This view is known as emergent space-time. It means that what we think of as geometry, length, distance, and duration might arise from the invisible structure of quantum information. In this model, time begins not with a bang, but with correlation. When enough systems interact in complex ways, an arrow of time appears. Cause and effect emerge. Memories form. change becomes perceptible, but underneath it all, there is no clock, only structure. If time is not real, what does that mean for our choices, for our memories, for our sense of self? These are not easy questions, but they remind us that human experience is layered. At one level, we are timeless, a configuration of matter and energy within a static universe. At another, we are temporal, beings who grow, learn, hurt, and hope. Both views may be true. Time may be an illusion, but it is a meaningful one. It gives shape to our stories, urgency to our actions, weight to our losses, and depth to our love. Without time, there is no change, and without change, there is no meaning. So even if physics tells us that time does not exist, that doesn't mean it isn't real to us. In the end, perhaps the point is not to answer whether time is fundamental, but to ask what time allows us to experience: the laughter of a friend, the growth of a tree, the turning of seasons, the first word of a child, the final breath of a life. These moments matter, not because they are eternal, but because they pass, because we live them once, and that fragility is what gives them beauty. So maybe time is a dream the universe is having, or maybe time is the dreamer, and the universe, its fleeting thought. We do not know, but we continue to ask, to wonder, to feel, and in that curiosity, in that ache to understand, we find something greater than any theory. We find presence, not the ticking of clocks, but the quiet sense of being here, now, and that, whatever it may be, is the closest we may ever come to touching time itself.